Far out in the depths of space, in a galaxy so distant its light has been traveling for more than 13 billion years to reach us, a star hundreds of times more massive than our Sun reaches the end of its life. Its core collapses, and in an instant, it unleashes a titanic blast of energy, a gamma-ray burst so powerful that it outshines its entire host galaxy, and for a few fleeting seconds, it becomes the brightest object in the entire observable universe. This is not a scene from science fiction. This is a real cosmic event, one of the most violent and enigmatic phenomena known to science. These bursts are the biggest explosions since the Big Bang itself, and they serve as brilliant beacons, illuminating the farthest frontiers of space and time. We are about to embark on a journey to the very edge of everything we can see, to explore 50 incredible facts about these most distant gamma-ray bursts. This is a voyage that will take us back to the cosmic dawn, to a time when the universe was in its infancy, and these colossal detonations were helping to shape the cosmos we inhabit today. Understanding these distant flashes is more than just cataloging cosmic curiosities. It is fundamental to our quest to understand our own place in the universe. Each gamma-ray burst is like a message in a bottle, hurled across the eons, carrying with it information about the conditions in the early universe, the formation of the first stars, and the very nature of matter and energy under the most extreme pressures imaginable. By studying them, we are essentially building a history of the cosmos, piecing together the story of how simple elements forged in the hearts of the first stars eventually coalesced into planets, and ultimately into life forms capable of looking back and wondering about it all. The detection of these events is a testament to human ingenuity and perseverance, requiring a global network of satellites and telescopes working in perfect harmony to catch a flicker of light that vanishes almost as soon as it appears. So prepare to have your perspective shifted. We will delve into the staggering energies involved, energies that dwarf the total output of our Sun over its entire 10 billion-year lifetime, released in a mere heartbeat. We will explore how astronomers use these bursts as cosmic yardsticks to measure the expansion of the universe itself, and we will confront the profound mysteries that remain, questions about what exactly triggers these cataclysms and what they can tell us about the ultimate fate of the cosmos. This journey to the edge of observation is a story of extremes, of discovery, and of the enduring human drive to reach out and comprehend the vast, beautiful, and often violent universe we call home. Let's begin our countdown of 50 facts, starting with the sheer, mind-bending power contained within a single, distant flash of light. To fully grasp the significance of these distant beacons, we must first understand what a gamma-ray burst actually is. At its most fundamental level, it is exactly what the name implies, a sudden, incredibly intense flash of gamma-ray light. Gamma rays are the most powerful form of energy in the electromagnetic spectrum, packing billions of times more energy than the visible light our eyes can see. Think of the difference between a gentle campfire and the entire detonation of a nuclear weapon. That's the kind of energy gap we're talking about. These bursts are not long, drawn-out affairs. They are incredibly brief, typically lasting anywhere from a few milliseconds to a couple of minutes. But in that fleeting moment, they become the most luminous events known to occur in the entire universe. The engine behind this unimaginable power is always a catastrophe of cosmic proportions. The most common type of burst, known as a long gamma-ray burst, is essentially the birth cry of a black hole. It occurs when a star dozens of times more massive than our Sun exhausts its nuclear fuel. Without the outward pressure from fusion to support it, the star's own immense gravity causes its core to collapse in on itself in a fraction of a second. This collapse forges a newborn black hole, and in the process, titanic jets of material and radiation are blasted outward at nearly the speed of light. If one of these ultra-focused jets happens to be pointed directly at Earth, We see it as a brilliant gamma-ray burst. The other primary cause is the collision of two incredibly dense stellar corpses like neutron stars. When these objects spiral into each other, they merge in a violent event that also creates a black hole and shoots out a similar, though typically shorter, blast of gamma rays. This is where the concept of distance transforms these events from mere explosions into something far more profound. Because light travels at a finite speed, when we look at an object that is incredibly far away, we are also looking back in time. The gamma ray burst from a galaxy 13 billion light-years away is a message that has been traveling for 13 billion years. We are witnessing an event that occurred when the universe was less than 1 billion years old, a mere infant by cosmic standards. This makes the most distant gamma ray burst some of the most valuable fossils we can study. They are not just explosions, they are direct probes into the era of the first stars, allowing us to observe the conditions and the violent processes that were shaping the early cosmos, long before our solar system even existed. Moving from the general mechanics of these cosmic explosions, we arrive at a specific event that perfectly exemplifies their role as probes into the deepest past. The record for the most distant gamma-ray burst observed belongs to an event designated GRB 090423, detected on April 23, 2009 by NASA's Swift satellite. This burst immediately stood out. Its fleeting gamma-ray signal, lasting about 10 seconds, was followed by a rapidly fading afterglow in infrared light. That afterglow was the crucial clue. Astronomers around the world raced to point their most powerful ground-based telescopes toward the coordinates provided by Swift. Measurements from telescopes like the Very Large Telescope in Chile confirmed what the faintness of the afterglow hinted at. This was no ordinary burst. The light from GRB 090423 had been traveling for an astonishing 13.1 billion years before it finally reached our detectors. To truly appreciate that number, we have to contextualize it within the entire history of the cosmos. The current best estimate for the age of the universe is approximately 13.8 billion years. This means the star that exploded to create GRB 090423 did so when the universe was only about 600 million years old. That period, known as the Era of Reionization, was a time of profound transformation. The first stars and galaxies were just beginning to ignite, burning away the primordial fog of neutral hydrogen that filled the universe after the Big Bang. To witness an event from this cosmic dawn is like finding a photograph of your own city taken within a few decades of its founding, a rare glimpse into its earliest and most formative years. This burst is not just an object at a great distance, it is a timestamp from an epoch that is incredibly difficult to observe directly. The significance of this detection cannot be overstated. It proved that massive stars, the kind that produce long gamma-ray bursts, were not only forming but also dying in spectacular supernova when the universe was less than 5% of its current age. This tells us that the first generations of stars, often called population 3 stars, must have included these behemoths. They lived fast and died young, seeding the early universe with the heavy elements forged in their cores and in their violent deaths. GRB 090423 is therefore more than a record holder. It is direct evidence of the intense, rapid star formation that occurred in the infancy of the cosmos. It shows that the universe was already a dynamic and violent place, capable of producing stellar catastrophes on a scale we can barely imagine, long before our own Milky Way galaxy had even taken its modern shape. Now, having encountered a blast from the cosmic dawn like GRB 090423, we need to address a fundamental question: how do astronomers actually know how far away these events are? The answer lies in a beautiful and fundamental consequence of our expanding universe, a phenomenon known as redshift. This concept is the master key that unlocks the vast distances of space and allows us to peer back through time itself. Imagine the universe not as a static stage, but as a rising loaf of raisin bread dough. As the dough expands, every raisin moves away from every other raisin. Now replace the raisins with galaxies and the dough with the fabric of space. Light traveling from a distant galaxy towards us is like a wave on that expanding fabric. As space itself stretches during the light's multi-billion-year journey, the wavelength of that light gets stretched along with it. This stretching has a direct and measurable effect on the light we receive. Visible light is made up of a spectrum of colors, from blue with shorter wavelengths to red with longer wavelengths. When the light from a distant object is stretched, its entire spectrum shifts toward the red end. This is the redshift. The degree of this shift is quantified by a number astronomers call Z. A higher redshift value directly corresponds to a greater amount of cosmic expansion that has occurred during the light's travel time, meaning the object is farther away and we are seeing it from an earlier epoch in the universe's history. For relatively nearby objects, the redshift might be a small number like Z equals 0.1, but for the truly distant denizens of the cosmos, the numbers become immense. This is where the most distant gamma-ray bursts truly boggle the mind. Events like GRB 090423 boast a redshift of approximately Z equals 8.2. To grasp what that means, consider that a redshift of Z equals 1 already corresponds to a time when the universe was about half its current age. A redshift of Z equals 8, however, catapults us back to a period when the universe was a mere 600 million years old. We have detected bursts with redshifts even greater than Z equals 9, pushing our view to within the first 500 million years after the Big Bang. This measurement isn't just a number on a page, it's a direct ticket to the universe's formative years. By analyzing the specific fingerprint of redshift in the afterglow of a gamma-ray burst, astronomers can not only pinpoint its incredible distance, but also use it as a probe to study the composition of the intergalactic medium it passed through, revealing the conditions of the early cosmos in a way that would otherwise be impossible. With our understanding of redshift firmly in place, we can now categorize the messengers themselves, because not all gamma-ray bursts are created equal. Astronomers quickly realized that these cosmic flashes could be sorted into two distinct families based on a simple but crucial measurement: how long the burst of gamma rays actually lasts. This division separates them into long-duration and short-duration gamma-ray bursts. The long bursts typically shine for more than 2 seconds, and many can last for a minute or even longer. In contrast, the short bursts are incredibly fleeting, often over in less than 2 seconds, with some lasting only a few thousandths of a second. This difference in duration is not arbitrary. It points directly to two completely different cosmic cataclysms happening in the distant universe. The source of a long gamma-ray burst is one of the most dramatic events imaginable. It is the final, explosive death of a truly massive star, often referred to as a collapsar. Picture a star that is 20, 50, or even 100 times more massive than our Sun. It lives a furious and short life, burning through its nuclear fuel in just a few million years. When that fuel runs out, the star's core can no longer support its own immense weight. It collapses catastrophically inward, and in that instant, a new black hole is born. The incredible forces involved then blast out jets of particles and radiation at almost the speed of light. If our planet is fortunate enough to be looking right down the barrel of one of those jets, we witness the spectacle of a long gamma-ray burst, the star's brilliant final farewell. Short gamma-ray bursts, on the other hand, have a different, though equally violent, origin story. These are not the death throes of a single massive star, but rather the explosive merger of two incredibly dense stellar corpses, neutron stars. Neutron stars are what remain after a star that wasn't quite massive enough to form a black hole goes supernova. They pack more mass than our Sun into a sphere only about the size of a city. When two of these objects become locked in a gravitational dance, slowly spiraling inward over billions of years, they eventually crash together in a spectacular collision. This merger also creates a black hole and sends out a blinding flash of gamma rays, but this flash is far briefer than its long-duration counterpart. These events are so powerful that they also ripple the fabric of spacetime itself, producing gravitational waves that we can now detect here on Earth. This distinction becomes profoundly important when we turn our gaze to the very edge of the observable universe, to the most distant gamma-ray bursts ever recorded. The vast majority of these far-traveled beacons are of the long-duration variety. The reason for this lies in the timeline of cosmic evolution. The early universe was a very different place. It was smaller, denser, and brimming with the raw hydrogen and helium gas needed to form the first stars. These first stars, known as population 3 stars, are thought to have been giants, many of them reaching sizes and masses far greater than any star we see in the universe today. They were the perfect progenitors for long gamma-ray bursts, living fast, dying young, and lighting up the cosmos with their spectacular final explosions. Neutron star mergers, which produce short bursts, require a much longer cosmic timescale to occur. First, you need stars to be born, live their lives, and go supernova, leaving behind neutron stars. Then, those neutron stars have to find a partner and begin their slow gravitational spiral, a process that can take billions of years. In the universe's first few 100 million years, there simply hadn't been enough time for this elaborate sequence of events to play out. Therefore, when we detect a gamma-ray burst with a redshift of 8 or 9, we are almost certainly witnessing the death of one of the universe's very first massive stars. Each long-duration burst from this era is a direct signal that the cosmic building blocks were being forged and scattered, paving the way for the richer, more complex cosmos that would follow. This staggering power leads us directly to one of the most difficult facts to truly comprehend about these distant events: their almost unimaginable energy output. To put it in the simplest terms, the numbers involved are so vast that they defy all earthly comparisons. In just a few seconds, a single gamma-ray burst from the edge of the observable universe can release more energy than our Sun will emit over the course of its entire 10 billion-year lifespan. Let that sink in for a moment. Our Sun, which bathes our entire solar system in light and heat, which drives our climate and makes life possible, will steadily output a colossal amount of energy over 10 billion years. A distant gamma-ray burst surpasses that total output in the time it takes you to snap your fingers. This isn't just an explosion. It is a fundamental restructuring of a small corner of the cosmos, a momentary puncture in the fabric of space-time, releasing energy on a scale that is almost pure mathematics. But this energy isn't just dumped indiscriminately into space like a bomb. The key to understanding how we can see these events from such incredible distances lies in the geometry of the explosion. The energy is not released in a spherical blast that dissipates equally in all directions. Instead, it is focused into two incredibly narrow, opposing jets of material and radiation that scream outward at more than 99.9% of the speed of light. Think of it not as a light bulb which illuminates a room in all directions, but as a cosmic lighthouse beam, or more accurately, a laser pointer of unimaginable power. This process, known as relativistic beaming, concentrates the phenomenal energy into a very small angle, perhaps only a few degrees wide. This concentration is what makes the burst so phenomenally bright along the axis of the jet. This beaming effect solves a major puzzle. If the energy of a gamma-ray burst were spread out evenly in all directions, the total energy required to make it visible from 13 billion light-years away would be so immense that it would challenge our understanding of physics. By focusing the power into narrow jets, the total energy budget, while still astronomical, becomes a bit more manageable within known physical models. It also introduces an element of chance to our observations. For us to witness a gamma-ray burst, one of those ultra-focused jets must be pointed precisely, and I mean precisely, in the direction of our solar system. We are, in effect, looking down the barrel of the universe's most powerful cannon. This means that for every burst we see, there are hundreds or even thousands of others happening all across the universe whose jets are aimed away from us, completely invisible to our telescopes. We are only seeing a tiny fraction of the total stellar catastrophes occurring in the cosmos. The implications of this focused energy beam are profound for the surroundings of the burst itself. Any planet unfortunate enough to be located within the narrow cone of a gamma-ray burst jet, even from thousands of light years away, would be sterilized. The intense radiation would scour its atmosphere, triggering chemical reactions that would produce nitrogen dioxide, effectively creating a perpetual, dark brown smog that would blot out the sun and lead to a global ice age, all while being bombarded by lethal ultraviolet radiation. Some scientists have even speculated that a nearby gamma-ray burst could have been responsible for a mass extinction event in Earth's own history, a reminder that the universe is not always a peaceful place. The fact that we can detect the light from such a violent event after it has traveled for over 13 billion years through the expanding universe is a testament not only to the raw power involved but also to the precise, focused nature of its delivery. It is a narrowly avoided catastrophe on a galactic scale, seen from the safest possible distance. While the initial flash of gamma rays is over in a heartbeat, the story is far from finished. In many ways, the main event is just the opening act for a much longer and more informative performance, one that astronomers call the afterglow. Imagine a firework exploding in the night sky. The initial burst is brilliant but brief. What follows, however, is the lingering, colorful glow that slowly fades, allowing you to study its shape and composition. A gamma-ray burst's afterglow operates on a similar principle, but on a cosmic scale and across the entire electromagnetic spectrum. This fading emission is the key that unlocks the true scientific potential of these distant events, turning a fleeting flash into a long-lasting cosmic laboratory. The creation of this afterglow is a violent and dramatic process. That initial jet of material traveling at almost the speed of light doesn't travel through a perfect vacuum. It immediately begins to slam into the tenuous wisps of gas and dust that surround the progenitor star, the interstellar medium. This collision is catastrophic. The leading edge of the jet plows into this material like a cosmic snowplow, creating a powerful shock wave. The particles caught in this shock wave are accelerated to tremendous energies, and as they are whipped around by magnetic fields within the blast, they begin to radiate. This radiation starts at the highest energies, producing an X-ray afterglow, and then gradually cascades down to lower energies, creating visible light, infrared, and finally, a radio wave afterglow that can persist for weeks or even months. This multi-wavelength nature of the afterglow is what makes it so invaluable. Each part of the spectrum tells a different part of the story. The X-ray afterglow, detected by space-based observatories like NASA, Swift, and Chandra telescopes, gives us a direct look at the heart of the explosion's mechanics, revealing details about the energy and composition of the jet itself. The optical and infrared afterglow, which can be tracked by giant ground-based telescopes like the Keck Observatory or the Hubble Space Telescope, is the real prize for measuring distance. As this light travels through the expanding universe, its wavelength is stretched or redshifted. By identifying familiar chemical fingerprints in the afterglow's spectrum and seeing how much they have been shifted toward the red, astronomers can calculate the precise redshift and therefore the exact distance to the burst. It was through this method that the incredible distance of GRB 090423 was confirmed. Furthermore, the way the afterglow fades over time provides a wealth of information about the environment where the star died. Is the fading smooth and rapid? This suggests the jet is expanding into a relatively uniform, low-density region of space. perhaps indicating the progenitor star had blown away much of its surrounding gas with fierce stellar winds before it exploded. Does the light curve show a sudden bump or a slow decline? This could be evidence of a dense shell of material nearby, or it might mean the jet is interacting with a cloud of gas that was ejected by the star in an earlier, less violent event. By carefully analyzing the brightness and behavior of the afterglow across different wavelengths, astronomers can effectively perform an archaeological dig on the stellar neighborhood, reconstructing the life and final moments of the star that created the burst, all from a signal that has journeyed for billions of years to reach us. Capturing these cosmic transients, especially the precious afterglows of the most distant bursts, is a race against time on an astronomical scale. This brings us to one of the most critical tools in modern astronomy, a space observatory that has fundamentally changed the game, NASA Neil Gehrels Swift Observatory, often simply called SWIFT. Before SWIFT's launch in 2004, studying gamma-ray bursts was a frustratingly slow process. A satellite might detect the initial flash of gamma rays, but relaying those coordinates to ground-based telescopes could take hours. By the time astronomers pointed their powerful instruments toward the sky, the crucial afterglow had often faded into nothingness, leaving the burst's origin and distance a permanent mystery. SWIFT was designed from the ground up to solve this exact problem, acting as a rapid response sentinel in the void. The genius of SWIFT lies in its name and its multi-wavelength eyes. The spacecraft carries 3 telescopes working in perfect harmony. The first is the Burst Alert Telescope, or BAT, which constantly scans over a sixth of the sky at any given moment, watching for the sudden telltale sign of a gamma-ray burst. The moment the BAT detects a burst, the entire satellite springs into action. This is where its revolutionary rapid slewing capability comes into play. Unlike most large telescopes that take a long time to carefully pivot, SWIFT is incredibly agile. It can autonomously and swiftly, hence its name, reposition itself to point its 2 other telescopes, the X-ray telescope and the ultraviolet/optical telescope, at the precise location of the burst. This entire complex maneuver, from initial detection to having the afterglow in the crosshairs of its secondary instruments, takes less than a minute. In the world of gamma-ray bursts, where every second counts, this speed is the difference between a major discovery and a missed opportunity. This rapid response is not just about speed for speed's sake. It is the key that unlocks the scientific treasure chest of the afterglow. By capturing the X-ray and optical light within the first critical minutes, SWIFT can pinpoint the location of the burst with astonishing accuracy, often narrowing it down to an area of the sky smaller than the apparent size of a grain of sand held at arm's length. It then immediately transmits this precise celestial coordinates to observatories all over the world and in space, triggering a global campaign of observation. Ground-based telescopes, from small robotic instruments to the colossal mirrors of the Keck and very large telescope arrays, receive the alert and swing into action, training their sights on the fading glow. This seamless handoff from space to ground is what has allowed us to measure the extreme redshifts of bursts like GRB 090423. Without SWIFT's lightning-fast initial fix, those distant afterglows would have vanished before we even knew where to look. The impact of this mission has been nothing short of transformative. In its nearly 2 decades of operation, SWIFT has detected over 1,000 gamma-ray bursts, providing a vast and statistically significant catalog that has allowed astronomers to move from studying individual curiosities to understanding the population as a whole. It was SWIFT data that solidified the connection between long bursts and the deaths of massive stars, and it has been instrumental in identifying the origins of short bursts in neutron star mergers. Furthermore, its ability to stare at the X-ray afterglow for days after the initial blast has revealed intricate details about the physics of the relativistic jets and the environments surrounding the progenitor stars. By serving as the universal alarm bell for the high-energy universe, Swift has not only found the most distant GRBs, but has given us the sustained, multi-wavelength view needed to understand what they truly are. Brilliant beacons from the universe's earliest chapters, guiding us toward a deeper comprehension of cosmic evolution. While Swift acts as the rapid response detective, pinpointing the location of a burst with surgical precision, another space observatory plays an equally vital role as the big-picture surveyor, capturing the initial fury of the explosion in breathtaking detail. This is the Fermi Gamma Ray Space Telescope, a powerhouse instrument designed to see the universe in the most energetic light imaginable. Whereas Swift's Burst Alert Telescope is excellent at catching bursts, Fermi's primary instrument, the Large Area Telescope, or LAT, has a much wider field of view. Think of it as the difference between looking through a telephoto lens and a wide-angle lens. Fermi sees a huge swath of the sky at once, making it incredibly proficient at detecting the initial pulse of gamma rays, often catching bursts that other satellites might miss. But its contribution goes far beyond mere detection. It measures the energy of these gamma rays with an accuracy that was previously unimaginable. This high-energy data is absolutely crucial because it reveals the fundamental physics happening within the relativistic jet itself. The initial flash of a gamma ray burst isn't a single, monolithic color of light. It's a complex spectrum of radiation with photons carrying vastly different amounts of energy. Fermi's LAT can measure these energies across a colossal range, from millions to hundreds of billions of electron volts. To put that in perspective, the energy of visible light is about 2 electron volts. Fermi is detecting particles with energies trillions of times greater. This allows scientists to see the highest energy component of the burst, which holds clues to the mechanisms that accelerate particles to such incredible speeds. By analyzing this spectrum, researchers can test theoretical models about the jet's composition, its magnetic fields, and the exact processes that turn gravitational collapse into a directed beam of pure energy. The real power, however, emerges when data from Fermi and Swift are combined. This partnership creates a complete multi-wavelength timeline of the entire event, from the first unimaginably energetic milliseconds to the fading afterglow that persists for days. Here's how it typically unfolds. Fermi's wide field of view often detects the initial gamma ray pulse first, providing an immediate alert that a cataclysm has occurred somewhere in the cosmos. Almost simultaneously, Swift's Burst Alert Telescope, which also constantly scans the sky, will detect the same event. Swift then executes its rapid slewing maneuver to pinpoint the location with extreme accuracy. As Swift's X-ray and optical telescopes lock onto the target and begin studying the evolving afterglow, Fermi continues to observe the high-energy emission, sometimes for hours after the initial trigger. This synergistic observation is like having a team of specialists analyzing a crime scene. Fermi is the expert who arrives first, assessing the initial blast zone and collecting evidence about the raw power of the explosion. Swift is the forensic investigator who arrives moments later, cordoning off the area and using specialized tools to gather minute details about the surroundings. Together, they build a profile of the event that neither could achieve alone. For instance, by comparing the timing of the highest energy photons detected by Fermi with the lower energy X-rays and light seen by Swift, astronomers can piece together the sequence of events within the jet, understanding how the shock waves propagate and evolve. This combined dataset has been instrumental in confirming that the observed light curves and spectra align with the predictions of the relativistic fireball model, the leading theory for how gamma-ray bursts work. For the most distant bursts, this partnership is particularly invaluable. When a signal arrives from the edge of the observable universe, it is inherently faint. Having two independent sets of measurements adds confidence to the analysis. Fermi's data can help confirm that the properties of a distant burst, like its total energy output and spectral characteristics, are consistent with being a scaled-up version of closer events, reinforcing the idea that the same physical laws govern the universe 13 billion years ago. The ability to study a single event across such a vast range of the electromagnetic spectrum, from Fermi's high-energy gamma rays down to the infrared afterglow measured by ground-based telescopes, turns each distant gamma ray burst into a complete cosmic laboratory. It provides a stringent test for our models of stellar death and black hole birth, ensuring that our understanding of these brilliant beacons from the cosmic dawn is built on the most robust and comprehensive data possible. Detecting these ancient signals is one of the greatest technical challenges in modern astronomy, a race against time and the fundamental limits of observation. The primary obstacle is sheer faintness. By the time the light from a gamma ray burst at the edge of the observable universe reaches us, it has been diluted by its 13 billion-year journey across an expanding cosmos. The photons are spread incredibly thin, like a single candle placed on the moon, viewed through Earth's atmosphere. The initial gamma-ray flash, while phenomenally powerful at its source, arrives at our satellites as a mere whisper, a faint tickle of high-energy particles that must be distinguished from background noise and other cosmic events. But that initial detection is only the starting pistol. The real scientific goldmine, the afterglow, is even fainter and fading fast. This is where the need for speed becomes absolutely critical. The moment a satellite like Swift or Fermi detects a burst, an automated alert is sent to a global network of observatories within seconds. Astronomers on the ground, often in the middle of their night, receive these alerts on their phones and computers, triggering a carefully orchestrated scramble. Large telescopes like the Keck Observatory in Hawaii or the Very Large Telescope in Chile are not simple point-and-shoot instruments. They are complex behemoths that require precise scheduling. To catch a gamma-ray burst afterglow, astronomers must submit urgent requests to interrupt their pre-planned observations, a process known as a target of opportunity. Every minute of delay means the afterglow is becoming exponentially dimmer, and with it, the chance to measure its redshift and unlock its secrets dwindles. It is a high-stakes partnership between autonomous satellites in space and nimble, responsive teams on Earth. The final, and perhaps most defining, challenge is what the expansion of the universe does to the light itself. For these incredibly distant bursts, the cosmological redshift is so extreme that it fundamentally changes the nature of the light we receive. The visible light that was emitted by the afterglow, what might have been blue or green or red light, has been stretched so dramatically during its long journey that it is no longer visible to our eyes or to standard optical telescopes. Its wavelength has been shifted all the way into the infrared part of the electromagnetic spectrum. This is not a minor adjustment. It means that the key diagnostic lines used to measure redshift, which for closer objects are found in the optical range, have been pushed deep into the infrared. This reality demands a completely different set of tools. Studying the most distant gamma-ray bursts requires powerful telescopes equipped with sophisticated infrared cameras and spectrographs. Ground-based infrared astronomy is notoriously difficult because Earth's atmosphere itself glows brightly in infrared, creating a noisy background that can easily swamp a faint cosmic signal. Furthermore, water vapor in the atmosphere absorbs specific infrared wavelengths, blocking our view. This is why the premier observations of high redshift burst afterglows are often conducted by space telescopes like the Hubble Space Telescope and now the James Webb Space Telescope. Operating above the obscuring effects of the atmosphere, these observatories can capture the pristine, faint infrared light of these ancient explosions with stunning clarity. The successful detection and analysis of a burst like GRB 090423 was a triumph of this multifaceted approach, combining rapid satellite detection with swift follow-up by the world's most powerful ground-based infrared telescopes and the unparalleled sensitivity of Hubble. It represents a monumental effort to stretch our observational capabilities to the very limit, all to decode a message from the cosmic dawn. Now we come to a truly transformative application of these distant cosmic explosions, one that elevates them from mere cataclysms to indispensable scientific tools. Beyond their incredible power and distance, gamma-ray bursts serve as the universe's ultimate flashlights. Imagine you are in a vast, dark forest at night, and for just a few seconds, a brilliant flash of lightning illuminates the entire landscape. In that fleeting moment, you can see the shapes of the trees, the path ahead, and the composition of the forest floor. A distant gamma-ray burst does exactly this for the cosmos. Its intense, focused beam of light travels for billions of years, and along its journey to us, it pierces through clouds of gas and dust within and between galaxies. This light doesn't just pass through this material unchanged, it interacts with it, and by analyzing the subtle fingerprints left on the light, astronomers can dissect the composition of the universe across immense spans of space and time. The key to this cosmic forensics is a technique called absorption spectroscopy. When the brilliant afterglow of a gamma-ray burst passes through a cloud of gas, the atoms within that cloud absorb specific wavelengths of light. Each element has its own unique absorption signature, a barcode of dark lines that appears in the spectrum of the light. By spreading the faint light of the afterglow into a rainbow of colors or a spectrum, and looking for these missing pieces, scientists can identify exactly which elements are present in the intervening gas clouds. This turns the gamma-ray burst into a backlight and the gas clouds into cosmic stained glass windows, each one filtering the light in a unique way that reveals its chemical identity. This is where the distance of the burst becomes critically important. When we study a gamma-ray burst from the cosmic dawn, we are not just analyzing the gas in its immediate host galaxy. We are capturing a snapshot of the entire line of sight back to Earth, a core sample through billions of years of cosmic history. The light from a burst like GRB 090423 has passed through the pristine intergalactic medium of the early universe, through the halos of ancient galaxies it encountered along the way, and finally through the more evolved gas of our own galactic neighborhood. The resulting spectrum is a layered timeline, with absorption lines from different redshifts telling the story of how the universe's chemical composition has evolved. The most distant lines, those with the highest redshifts, provide a direct measurement of the conditions when the universe was only a few 100 million years old. One of the most crucial measurements this technique provides is metallicity, a term astronomers use for the abundance of any element heavier than helium. In the context of the early universe, this is a profound concept. After the Big Bang, the universe was composed almost entirely of hydrogen and helium. Every single atom of carbon, oxygen, iron, gold, and every other heavy element had to be forged later, in the nuclear furnaces of stars and in the violent explosions of supernova and gamma-ray bursts themselves. Therefore, the metallicity of a gas cloud is a direct record of past stellar activity. Finding heavy elements in a cloud from the cosmic dawn tells us that an entire generation of stars must have already lived, died, and enriched their surroundings with these newly created elements. The data from distant gamma-ray burst afterglows has delivered a startling revelation. Even in galaxies that existed when the universe was less than 1 billion years old, astronomers have detected the clear signatures of elements like silicon, carbon, iron, and oxygen. This means that the first stars, the mythical population 3 stars, had already completed their life cycles, seeding their host galaxies with the building blocks of planets and life incredibly quickly after the Big Bang. The universe did not remain pristine for long. It became chemically enriched with astonishing speed. These measurements are incredibly difficult to make by any other means, as normal galaxies from that epoch are far too faint to study in such detail. The brilliant flash of a gamma-ray burst provides the only light source powerful enough to conduct this chemical analysis on the universe's infancy. offering a unique window into the dawn of the elements that would one day form our own world. This connection between the most distant gamma-ray bursts and the universe's first stars brings us to one of the most compelling theories in modern cosmology. The cataclysmic explosions we witness from the cosmic dawn are increasingly seen as the direct death cries of a type of star that has never been observed directly, a stellar population that existed only in theory until recently. These are known as Population 3 stars, the true pioneers of the cosmos. The name comes from a simple classification system. Population 1 stars, like our Sun, are metal-rich and found in the disks of spiral galaxies. Population 2 stars are older, metal-poor stars found in galactic halos and globular clusters. Population 3, then, represents the very first generation, the stars that ignited from the primordial soup of hydrogen and helium created by the Big Bang. They were the universe's first light, and their properties were likely unlike anything we see today. The defining characteristic of these first stars was their purity. They formed from gas that had not yet been polluted by the ashes of previous stellar explosions. Without any heavy elements to help cool the gas clouds through radiation, the prevailing theory suggests that these clouds could collapse into much more massive structures than what is possible in the modern universe. While today the average star might be similar in mass to our Sun, Population 3 stars are thought to have been true behemoths with masses ranging from several dozen to even 1,000 times the mass of our Sun. Imagine a star so colossal that it would make our Sun look like a mere speck in comparison. These stars would have lived incredibly fast and furious lives, burning through their nuclear fuel in only a few million years, a mere blink in cosmic time, before meeting a spectacular end. This is where the link to long-duration gamma-ray bursts becomes so powerful. We know from observations in our local universe that long GRBs are associated with the core collapse of massive, rapidly rotating stars. A Population 3 star with its enormous mass is the perfect candidate to produce the most extreme version of this phenomenon. Its immense gravity would lead to a catastrophic collapse far more energetic than any supernova we see today. The resulting formation of a black hole and the launch of relativistic jets would be a fitting final act for a star of such legendary proportions. Therefore, when we detect a gamma-ray burst from a redshift of 8 or 9, we are likely witnessing the signature of a Population 3 star's death. It is the only known astrophysical process violent enough to be visible from such incredible distances, and the timing aligns perfectly with the era when these first stars were ending their short lives. The significance of this goes far beyond simply spotting a rare type of star. The death of these Population 3 giants was a transformative event for the entire cosmos. During their brief lives, they fused hydrogen and helium into heavier elements like carbon, oxygen, and silicon in their cores. But it was in their violent deaths as gamma-ray bursts and supernova that these newly forged elements were blasted out into space. This process, known as nucleosynthesis, was the universe's first act of cosmic recycling. The pristine intergalactic medium, which had been composed solely of hydrogen and helium, was suddenly seeded with the first traces of the elements that would one day become the building blocks of planets and ultimately life itself. Evidence from the afterglows of distant bursts strongly supports this narrative. When astronomers analyze the spectra of these afterglows, they look for the absorption lines caused by heavy elements in the host galaxy. In several high redshift bursts, they have indeed detected these signatures. Finding carbon, oxygen, magnesium, and silicon in a galaxy that existed when the universe was only a few 100 million years old is a smoking gun. It tells us that at least one generation of stars had already lived, died, and enriched their environment by that time. The gamma-ray burst itself is the exclamation point at the end of that sentence, the final, explosive act that dispersed those elements far and wide. Each distant GRB we detect is therefore not just a record of a single star's death, but a marker of a fundamental phase in cosmic evolution, the moment the universe began its long journey from a simple, pristine state to the chemically rich and complex cosmos we inhabit today. The incredible journey of light from a gamma-ray burst at the edge of the observable universe does more than just reveal the explosion itself. It acts as a brilliant probe, illuminating one of the most important and poorly understood periods in cosmic history. This era is known as the Epoch of Reionization, and the most distant gamma-ray bursts offer a unique window into this pivotal transition. For the first several 100 million years after the Big Bang, the universe was a much darker place. It was filled with a thick, pervasive fog of neutral hydrogen gas. Neutral hydrogen atoms are very effective at absorbing the high-energy, ultraviolet light that hot, young stars emit. So, even as the very first stars and galaxies began to flicker on, their light couldn't travel very far. The universe was trapped in what astronomers often call its cosmic dark ages, a time when the cosmos was opaque, shrouded in this primordial mist. The Epoch of Reionization was the process that cleared this fog. As more and more of the first massive stars ignited, their intense ultraviolet radiation began to blast apart the neutral hydrogen atoms, stripping away their electrons in a process called ionization. Think of it as a cosmic sunrise happening in slow motion over hundreds of millions of years. Vast, growing bubbles of ionized, transparent gas began to form around the first clusters of stars and galaxies. These bubbles eventually overlapped and merged until the entire universe became mostly transparent to light, a state it has remained in ever since. This was the moment the universe turned the lights on for good, allowing light to travel freely across vast cosmic distances for the first time. Understanding exactly how and when this happened is a major goal of modern cosmology, and this is where gamma-ray bursts become such powerful tools. The key lies in the absorption spectrum of a gamma-ray burst's afterglow. As that beam of light travels toward us, it passes through the intergalactic medium. If it passes through a region of neutral hydrogen, specific wavelengths of the light, particularly in the ultraviolet part of the spectrum, will be absorbed, creating a distinct feature known as the Lyman alpha forest. However, when the light from the most distant bursts, those from within or just after the reionization era, is analyzed, something remarkable happens. For light that was emitted when the universe was still largely neutral, the absorption is so complete that it creates a dramatic drop-off in the spectrum, a feature known as the Gunn-Peterson trough. It's like seeing a shadow cast by the primordial fog itself. The exact properties of this trough, how sharp the cutoff is, at what wavelength it begins, provide direct measurements of the fraction of neutral hydrogen that was still present at that specific moment in time. Each distant gamma-ray burst we detect gives us a single data point, a measurement of the transparency of the universe at the specific time the burst went off. By collecting data from bursts at slightly different redshifts, say at z equals 8, 9, and 10, astronomers can begin to build a timeline of reionization. It's like taking core samples from different depths in an archaeological dig. Each sample tells you about the conditions at a different point in history. A burst from z equals 10 might show a very deep Gunn-Peterson trough, indicating the universe was still mostly foggy. A burst from z equals 7 might show a much shallower trough, revealing that the process of reionization was nearly complete. This allows scientists to map the progress of this cosmic clearing, determining whether it happened quickly or slowly, and what kind of sources, whether early galaxies or perhaps even the first gamma-ray bursts themselves, provided the dominant ionizing power. This makes gamma-ray bursts far superior to ordinary galaxies for studying this era. Galaxies from the reionization epoch are extremely faint and difficult to detect. Their light is also emitted over a wide area, making it hard to get a clean absorption spectrum of the intergalactic medium in front of them. A gamma-ray burst, however, is an incredibly bright point-like source. Its light acts as a pristine, powerful flashlight beam that pierces through the cosmos, providing a much clearer and more sensitive spectral fingerprint. The discovery of a gamma-ray burst from within the heart of the reionization era is like finding a super-bright street lamp in the middle of a dense fog bank. It allows us to see the structure and density of the fog in exquisite detail along our entire line of sight. As new observatories like the James Webb Space Telescope come online, their ability to study the infrared afterglows of these ancient bursts will sharpen our view of this cosmic dawn, turning these cataclysmic explosions into our most precise probes for understanding how the early universe emerged from darkness into light. While our journey to the edge of the observable universe has been dominated by the colossal deaths of massive stars, there is another, rarer type of cosmic cataclysm that plays an equally crucial role in building the cosmos: the short gamma-ray burst. These fleeting flashes, over in less than 2 seconds, have a very different origin story that is just as violent but unfolds on a much smaller, denser scale. They are the signature of the ultimate cosmic collision, the moment when two neutron stars, the incredibly dense cores of dead stars, finally spiral together and merge. This merger is not just an explosion, it is a cosmic alchemy experiment of unparalleled ferocity, and it is now understood to be the primary source of the heaviest elements in the universe, including the gold in your jewelry and the platinum in catalytic converters. To understand the kilonova, we must first appreciate the extreme nature of neutron stars. These are the remnants of stars that were too massive to end their lives as white dwarfs, but not quite massive enough to collapse entirely into black holes. When such a star goes supernova, its core is crushed under unimaginable gravity. The force is so immense that protons and electrons are forced together, merging into neutrons. The result is a city-sized object that packs more mass than our Sun into a sphere only about 12 miles across. A single sugar cube-sized piece of a neutron star would weigh as much as a mountain. When two of these incredible objects become gravitationally bound, they slowly lose energy by emitting gravitational waves, inching closer together over billions of years until their final destiny, a head-on collision. The moment of merger is unimaginably violent. As the neutron stars touch, they rip each other apart in a fraction of a second, flinging a small but significant fraction of their material out into space at speeds approaching the speed of light. It is within this hot, expanding cloud of neutron-rich debris that the magic happens. Atomic nuclei are bombarded by a dense shower of neutrons in a rapid process aptly named the R process, or rapid neutron capture process. Normal nuclear fusion inside stars creates elements up to iron, but it cannot produce heavier elements efficiently. The R process, however, allows nuclei to gobble up neutrons so quickly that they become extremely heavy and unstable, then radioactively decay into stable forms of the heavy elements we know on Earth. In the heart of this cosmic maelstrom, in a matter of seconds, the seeds for elements like gold, platinum, uranium, and neodymium are forged. The visual manifestation of this process is the kilonova, a phenomenon thousands of times brighter than a typical nova but dimmer than a supernova. The radioactive decay of all these newly created heavy elements powers a brilliant, short-lived glow that peaks in infrared light. This is because many of these elements are opaque, so they trap the heat and re-radiate it at longer wavelengths. The historic first observation of a kilonova in 2017, associated with the gravitational wave event GW 170817, and the short gamma-ray burst GRB 170817A, confirmed this theory spectacularly. Observations showed that the event had produced an amount of gold and platinum equivalent to several times the mass of our entire planet, proving that the universe's jewelry box is filled by these spectacular collisions. The connection to the early universe, while more tenuous than for long bursts, is profound. For a kilonova to occur, a binary system of massive stars must first be born, live out their lives and explode as supernova, leaving behind two neutron stars that must then spiral together. This entire process takes billions of years. Therefore, detecting a short gamma-ray burst from the cosmic dawn is incredibly challenging, as the universe simply hadn't been around long enough for many of these systems to complete their dance. However, computer simulations suggest that under the dense, chaotic conditions of the early universe, some neutron star pairs could have formed and merged much more rapidly. Finding a high redshift short GRB would be a monumental discovery, indicating that the universe began minting its heavy elements even earlier than we thought. This changes our perspective on cosmic chemical evolution. While the first massive stars and their associated long GRBs produced the essential lighter elements like carbon and oxygen that are the bedrock of life, it is the kilinovae from short GRBs that are responsible for seeding the cosmos with the very heaviest atoms. Every time you hold a piece of gold, you are holding a tiny piece of a cataclysm that happened billions of years ago, the remnant of a neutron star collision that likely occurred long before our own solar system was even a cloud of gas and dust. These events, though less frequent and less luminous than their long-duration cousins, are therefore indispensable architects of the complex, element-rich universe we see today. They complete the periodic table, ensuring that the cosmic forge operates across the entire spectrum of matter. Yet even within the established families of long and short bursts, there exists a peculiar and mysterious outlier that continues to puzzle astronomers, the ultra-long gamma-ray burst. As the name implies, these events defy the typical duration limits, shining not for seconds or minutes, but for thousands of seconds, sometimes lasting for several hours. This extraordinary longevity points to an engine that is fundamentally different, a cosmic power source that can sustain its furious output for a vastly extended period. Understanding what could possibly fuel such a prolonged cataclysm has led scientists to propose some of the most dramatic scenarios in all of astrophysics. One leading theory suggests that the progenitor of an ultra-long burst isn't a typical massive star, but something even larger and more unstable, a blue supergiant. Most massive stars that produce long GRBs are thought to be Wolf-Rayet stars, which have shed their outer hydrogen envelopes through powerful stellar winds, leaving a compact, helium-rich core. When such a star collapses, the resultant jet has a relatively straightforward path to blast its way out, leading to a burst that typically lasts less than 100 seconds. A blue supergiant, however, is a behemoth that has retained its enormous hydrogen envelope. This creates a star with a radius that can be tens or even hundreds of times larger. If the core of such a star collapses, the relativistic jet faces a much longer and more arduous journey to escape the stellar interior. It must drill through this immense shroud of gas, a process that could take hours, explaining the greatly extended duration of the gamma-ray emission as the jet struggles to break free. An even more exotic and violent explanation involves the immense gravitational pull of a supermassive black hole. In this scenario, an ordinary star, perhaps similar to our Sun, wanders too close to the black hole lurking at the center of its galaxy. The tidal forces from the black hole are so overwhelming that they stretch and rip the star apart in a phenomenon known as a tidal disruption event. While most such events result in a flare of radiation as the stellar debris is accreted by the black hole, theorists suggest that under the right conditions, specifically, if the black hole is spinning rapidly and has a strong magnetic field, it could launch a relativistic jet from the stellar debris. This jet, powered by the slow and methodical feeding of the black hole on the remains of the star, could potentially produce a sustained burst of gamma rays lasting for thousands of seconds, matching the profile of an ultra-long GRB. When we turn our gaze to the most distant reaches of the universe, the story of ultra-long bursts becomes even more intriguing. detecting an ultra-long event from the cosmic dawn is incredibly challenging because their prolonged emission requires satellites to stare at a single patch of sky for hours, which can be difficult with the scanning patterns of observatories like Swift. Furthermore, the extreme redshift would stretch the signal, potentially moving the longest duration emission into a wave band that is harder to monitor continuously. So far, confirmed ultra-long GRBs have been found at more moderate distances within the observable universe. However, their very existence opens up a fascinating possibility. If the first stars included blue supergiants of unprecedented size, their collapse could have produced ultra-long bursts that were, for a time, the most persistent sources of light in the young cosmos. Finding such an event would be a direct probe into the upper limits of stellar size in the early universe, revealing just how colossal the first stars could become. The hunt for these outliers is more than a quest to catalog cosmic oddities. It is a pressure test for our models of stellar evolution and death. Each new ultra-long GRB detected provides critical data that helps astronomers distinguish between the blue supergiant and tidal disruption event hypotheses. The properties of the afterglow, for instance, can reveal the density of the environment around the explosion. A burst occurring in the dense central region of a galaxy near a supermassive black hole would have a different afterglow signature than one occurring in a remote stellar nursery where a massive star lived and died. As our monitoring capabilities improve with future missions, the potential to catch an ultra-long burst from the epoch of the first stars remains a tantalizing goal. It represents a chance to witness a truly extreme form of stellar death, one that pushes the boundaries of physics and deepens our understanding of the diverse ways the universe can produce its most brilliant flashes. While the expansion of the universe stretches and dims the light from our most distant targets, nature itself provides a remarkable tool to counteract this fading, a phenomenon predicted by Einstein's theory of general relativity known as gravitational lensing. This effect turns the fabric of spacetime into a vast natural telescope, one that can, under the right cosmic alignment, magnify the light of objects lying far behind it. The principle is elegant. Massive objects like galaxies or galaxy clusters warp the space around them. When light from a distant source, such as a gamma-ray burst, travels through this warped region on its way to Earth, its path is bent, much like light passing through a glass lens. This bending can focus the light, making the distant object appear significantly brighter and sometimes even creating multiple images of the same source. For observers hunting the faintest signals from the edge of time, this cosmic magnifying glass is a game changer. A typical gamma-ray burst from the cosmic dawn is already at the very limit of what our most powerful telescopes can detect. Its afterglow is an incredibly faint whisper, a challenge to capture even with hours of observation on the world's largest instruments. But if that same burst happens to lie directly behind a massive foreground galaxy cluster, the gravitational lens can amplify its light, sometimes by a factor of 10, 50, or even more. This sudden boost in brightness can be the difference between a successful measurement of the burst's redshift and a complete miss. It effectively gives our telescopes a free upgrade in power, allowing us to see details in the afterglow spectrum that would otherwise be lost in the noise, and potentially revealing bursts that are so far away they would be completely invisible without this natural assist. The search for these lensed events adds a new layer of strategy to the hunt for distant gamma-ray bursts. When a satellite detects a burst, astronomers immediately check its position against maps of known massive galaxy clusters. If the burst's coordinates align with one of these cosmic lenses, the excitement level skyrockets. The follow-up observations then become a race to capture not just a fading afterglow but a magnified one. The light curve and the spectrum of a lensed afterglow can exhibit telltale signatures, such as an unexpected brightness or even multiple peaks in the light, as different lensed images of the same event arrive at slightly different times due to the varied paths the light has taken around the lens. The potential of this technique is staggering. It could allow us to push our observational horizon even further back, potentially spotting gamma-ray bursts from the first 200 million years of the universe, a time when the very first stars were just beginning to ignite. These bursts would be standard candles from an epoch that is currently almost entirely dark to our direct view. Furthermore, the lensing effect itself provides valuable scientific data. By analyzing how the light is bent, astronomers can map the distribution of matter, both visible and dark, within the foreground lensing cluster. This means a single-lensed gamma-ray burst does double duty. It acts as a probe of the extreme stellar deaths in the early universe, while simultaneously helping us weigh and understand the invisible dark matter that dominates the mass of the cosmos. It turns a fleeting cataclysm into a tool for studying two profound mysteries at once. The extreme distances of these cosmic explosions lead us directly to a powerful tool that astronomers use to understand their true power, a tool born from meticulous observation rather than pure theory. This is the Amati relation, a fascinating and surprisingly consistent pattern that connects two key properties of a gamma-ray burst. It's an empirical correlation, meaning it was discovered by looking at the data from many bursts, not predicted by a specific model. The relation states that there is a direct link between the intrinsic energy of a burst, the total energy it releases in gamma rays corrected for its distance, and the peak energy of its spectrum. In simpler terms, the more energetically powerful a burst is at its source, the higher the energy of its individual gamma-ray photons will be. It's a bit like noticing that in a forest, the larger a tree is, the thicker its trunk tends to be. It's not a strict law of physics, but a very strong and useful trend seen in nature. This correlation is incredibly valuable because it acts as a kind of cosmic ruler. For a gamma-ray burst with a known distance, measured through the redshift of its afterglow, astronomers can easily calculate its intrinsic energy. But for bursts where the afterglow is too faint to measure a redshift, the Amati relation offers a potential shortcut. By carefully analyzing the properties of the gamma-ray light itself, specifically, the distribution of photon energies, scientists can estimate the peak energy of the spectrum. They can then use the Amati relation to make an educated guess about the burst's intrinsic energy. While this doesn't provide a precise distance on its own, it helps categorize the burst and indicates whether it is a nearby event or a potential candidate for an extremely distant, high-energy cataclysm, guiding decisions about which targets deserve precious follow-up telescope time. This brings us to the critical question of whether the most distant gamma-ray bursts, those messengers from the cosmic dawn, obey this rule established by their closer cousins. The answer is not straightforward and lies at the heart of active research. On one hand, the fact that we can detect these ancient bursts at all suggests that the fundamental physics behind the relativistic jet and its emission mechanism must be remarkably similar across cosmic time. The Amati relation seems to hold, at least approximately, for many high redshift bursts, which is a profound confirmation that the laws of physics were operating in the same way 13 billion years ago as they are today. The universe's most powerful explosions appear to follow a consistent blueprint, whether they happened last week or when the first galaxies were forming. However, there are intriguing hints that the most extreme bursts might be pushing the boundaries of this relation. Some studies suggest that the highest redshift gamma-ray bursts, those with redshifts beyond 8, might lie slightly off the main trend defined by closer events. They could be either more energetic for their spectral peak or have a slightly different spectral shape. There are a few compelling explanations for why this might be the case. One possibility involves the progenitor stars themselves. If the first stars were indeed metal-poor behemoths, as we suspect, their collapse could produce jets that are in some way cleaner or more efficient, leading to a subtle shift in the energy correlation. Alternatively, the extreme cosmological redshift itself stretches the observed spectrum so dramatically that accurately reconstructing the original, emitted peak energy becomes an immense challenge, introducing uncertainties that could make the burst appear to deviate from the relation. Studying the Amati relation in the context of the early universe is therefore a powerful test of our understanding of stellar evolution and high-energy physics. Each new distant gamma-ray burst detected adds a precious data point to this cosmic graph. If a clear pattern of deviation emerges, it would be a direct signal that the conditions in the early universe, the initial mass function of stars, the strength of magnetic fields, or the density of the surrounding environment, were different enough to leave a fingerprint on the explosions themselves. The Amati relation transforms from a simple measuring stick into a diagnostic tool, allowing us to peer not just at the distance of these bursts, but into the very nature of the stars that created them, revealing how the universe's most violent phenomena have evolved over billions of years. But identifying these host galaxies is one of the most daunting challenges in observational astronomy. When a gamma-ray burst fades, what remains is an incredibly faint smudge of light, a galaxy so distant that its own starlight is feeble even to our most powerful telescopes. The race to capture this light is a painstaking process. Astronomers must wait for the brilliant afterglow to completely vanish, which can take weeks or months, and then take extraordinarily long exposure images of the exact same patch of sky, patiently collecting photons over many hours to build up a signal from the underlying galaxy. It is like trying to spot a firefly next to a fading spotlight from miles away. You have to wait for the spotlight to die out completely before you can have any hope of seeing the faint, persistent glow of the firefly itself. What these observations reveal are galaxies that are truly primordial. They are small, compact, and undergoing ferocious bouts of star formation. Compared to a grand spiral galaxy like our Milky Way, which forms stars at a sedate pace of 1 or 2 per year, these host galaxies are stellar factories, churning out new stars at a rate that can be hundreds of times faster. They are building themselves up rapidly, but they are also incredibly immature. Their chemical makeup, inferred from the faint light we can capture, shows they are metal-poor, meaning they contain only a small fraction of the heavy elements found in modern galaxies. This fits perfectly with the picture of a young universe that has only recently begun to be seeded with the elements forged in the first generations of massive stars. The galaxy that hosted a burst like GRB 090423 was likely a clumpy, turbulent place, a cosmic construction site where giant stars were being born and dying in quick succession, their violent deaths clearing out gas and enriching their surroundings with the raw materials for future planets. This is where the connection to the James Webb Space Telescope becomes so powerful. Webb is not specifically a gamma-ray burst hunter. Its strength lies in its unprecedented sensitivity in the infrared, allowing it to see the earliest galaxies directly. And what it has found is a universe teeming with small, bright, and surprisingly mature galaxies at very high redshifts, existing even earlier than we thought possible. When we compare the properties of these early Webb galaxies to the host galaxies of distant gamma-ray bursts, we see a fascinating overlap. Both populations are small, intensely star-forming, and exist in the same cosmic epoch. This provides crucial context. It tells us that the galaxies capable of producing long gamma-ray bursts were not bizarre outliers. They were likely typical members of the early galaxy population. The gamma-ray burst is simply the most dramatic symptom of the intense star-forming activity that was commonplace in the young cosmos. However, there might be a key difference that makes a galaxy particularly prone to hosting these cataclysms. Beyond just rapid star formation, theorists suggest that a low abundance of heavy elements or low metallicity might be a crucial ingredient. The reasoning is that stars with fewer heavy elements lose less of their mass through powerful winds during their lives. This allows them to retain more of their mass and, crucially, their rapid rotation right up to the moment of their death. A fast-spinning core is thought to be essential for launching the narrow, relativistic jets that characterize a gamma-ray burst. Therefore, the host galaxies of the most distant GRBs might represent a specific subset of the early universe population, those that are not just forming stars quickly, but are also the most chemically primitive, preserving the pristine conditions that allow for the formation of the unstable stellar giants whose deaths illuminate the cosmos. Each identified host galaxy is therefore a double clue, telling us about both the environment of the burst and the specific conditions that governed star formation in the universe's first chapters. The arrival of the James Webb Space Telescope marks a seismic shift in our ability to decode these ancient signals, acting as a time machine perfectly calibrated for the deepest cosmos. While telescopes like Hubble have been instrumental in studying gamma-ray burst afterglows, they eventually hit a wall when the light from the most distant events is redshifted so far that it vanishes from the optical and even near-infrared range, moving into the mid-infrared. Webb's mirrors are specifically designed to see this deeply redshifted light with stunning clarity, operating at temperatures only a few tens of degrees above absolute zero to ensure its own heat doesn't swamp the faint cosmic signals it's designed to capture. This is like moving from a standard microphone to a super-sensitive parabolic dish. We are now hearing whispers from the early universe that were previously inaudible. For a distant gamma-ray burst, this capability is transformative. When Webb receives an alert from satellites like Swift, it can swiftly point its massive gold-coated mirror toward the fading afterglow. Its suite of instruments, particularly the near-infrared spectrograph, can then dissect the infrared light with a level of detail that was once impossible. Where previous observations might have detected a faint smudge, Webb can spread that light into a rich, high-resolution spectrum, revealing a forest of absorption lines from elements like oxygen, carbon, and silicon in the host galaxy and the intergalactic medium along the line of sight. This isn't just confirming the presence of heavy elements, it's allowing scientists to measure their precise abundances, effectively taking a core sample of the chemical environment in a galaxy that existed when the universe was only a few 100 million years old. The insights gained are already profound. Webb's observations are confirming that these early galaxies, while primitive, were already surprisingly chemically complex. The detection of specific elements and even molecules provides a detailed history of the star formation that preceded the gamma-ray burst itself. For instance, the ratio of different elements can reveal the types of stars that lived and died in that galaxy. A high abundance of oxygen compared to iron might suggest that the galaxy was dominated by short-lived massive stars whose deaths enriched the gas quickly. Webb's power allows us to move from simply knowing that a galaxy had heavy elements to understanding the specific sequence of stellar life and death that produced them, turning each gamma-ray burst site into a detailed archaeological dig. Beyond just the burst itself, Webb's unparalleled vision is giving us our first clear look at the host galaxies of these cataclysms. Before Webb, these galaxies were often just faint, unresolved blobs. Now we can begin to study their structure, size, and the distribution of their star-forming regions. We can ask, was the gamma-ray burst located in a central, intense starburst region or on the outskirts of a smaller, merging galaxy? This contextual information is vital for understanding the conditions that lead to the formation of the unstable stellar progenitors of these bursts. By correlating the properties of the explosion with the detailed characteristics of its host, Webb is helping to answer fundamental questions about whether these events require a specific type of galactic environment, further refining our understanding of how the first stars and galaxies co-evolved to shape the cosmos we see today. But for all their incredible power, these cosmic beacons face a formidable enemy on their journey to our telescopes, a subtle thief of light that can render the most distant explosion virtually invisible. This challenge is known as dust extinction, and it represents one of the most significant obstacles in our quest to map the farthest reaches of the universe. Imagine a brilliant lighthouse on a distant shore. On a clear night, its beam cuts across the water, visible for miles, but on a foggy evening, that same light is diffused, dimmed, and reddened, its true intensity masked by the haze. Interstellar and intergalactic dust acts in much the same way for the light of a gamma-ray burst. These microscopic grains of carbon and silicon, forged in the hearts of stars and scattered by their deaths, are scattered throughout galaxies, including our own. When the light from a burst's afterglow passes through these clouds, the dust doesn't just block the light. It selectively absorbs it with a strong preference for shorter, bluer wavelengths. This selective absorption has a dramatic effect on our observations. The afterglow of a gamma-ray burst, when first emitted, is actually incredibly blue and bright across the optical spectrum. But as that light travels through dusty regions in its host galaxy, and then again through the dust of our own Milky Way, the blue light is scavenged away. What finally reaches us is a much redder and, critically, a much dimmer version of the original signal. For a burst that is already extraordinarily faint due to its immense distance, this additional dimming can be the difference between a successful detection and a complete miss. The very signature we rely on to measure distance, the sharp, identifiable features in the optical spectrum, can be smoothed out and weakened to the point of being unrecognizable, lost in the murky red glow. A burst that could have been a new record holder might simply fade into the background noise of the sky, its profound message from the cosmic dawn forever undelivered. This creates a serious selection bias in our catalog of distant gamma-ray bursts. Essentially, we are far more likely to detect and successfully measure the redshift of bursts that happen to occur in relatively dust-free environments or whose path to us is fortuitously clear. It's akin to trying to understand the population of a city by only interviewing people who live on main streets, completely missing everyone who resides in the back alleys. If the most ancient galaxies were particularly dusty places, perhaps due to intense early generations of star formation, we could be missing a significant fraction of the gamma-ray bursts from that era. Our view of the early universe, therefore, might be skewed toward those regions that had already been cleared out by previous stellar activity, giving us an incomplete picture of the true diversity of environments at the cosmic dawn. The fight against dust extinction is a constant battle for astronomers, fought with advanced technology and sophisticated data analysis. The first line of defense is to observe the afterglow in infrared light. Since dust is more transparent to longer wavelengths, the infrared portion of the afterglow suffers less extinction. This is why observatories like the Spitzer Space Telescope and now the James Webb Space Telescope are so crucial. They see the light that the dust lets through. Furthermore, when analyzing the data, astronomers can carefully measure the color of the afterglow. By quantifying how much redder it appears than expected, they can estimate the amount of dust along the line of sight and mathematically correct for its dimming effect, a process called deridening. This allows them to reconstruct the burst's intrinsic brightness and obtain a clearer, though still challenging, view of its spectral features. Despite these efforts, the threat of dust remains a sobering reminder that for every brilliant beacon we catch from the edge of time, there may be dozens of others whose light has been effectively extinguished by the very cosmic debris that their own kind helped to create. This incredible concentration of energy brings us to a truly fundamental concept, one that answers a question you might have been asking yourself. How is it even possible for us to see a single star explode from the other side of the observable universe? The answer lies in a phenomenon known as relativistic beaming, often called the lighthouse effect. Think of it this way: if you take a colossal amount of energy and release it in a giant spherical explosion, that energy spreads out evenly in all directions. By the time it travels 13 billion light-years, it would be so diluted and faint that our telescopes would never notice it. But a gamma-ray burst doesn't explode like a bomb. It functions more like a cosmic blowtorch, channeling its unbelievable power into two incredibly narrow opposing jets. These jets are so focused that they might only be a few degrees wide, a fraction of the space in the sky. This is the secret. Instead of illuminating the entire cosmos, the burst focuses its light into a pair of brilliant, narrow beams, like a lighthouse on a distant, stormy coast. The material in these jets isn't just moving quickly. It's traveling at a significant fraction of the speed of light, what physicists call relativistic speeds. At these velocities, strange and wonderful things happen to the light itself, as predicted by Einstein's theory of special relativity. The radiation generated by the jet gets beamed forward, concentrated intensely along the direction of motion. This is similar to how the sound of a supersonic jet seems to be concentrated in a cone behind it, a sonic boom. In the case of a gamma-ray burst, this relativistic beaming further amplifies the brightness of the jet along its axis, making it appear vastly more luminous to any observer lucky enough, or perhaps unlucky enough, to be looking straight down the barrel. This combination of a narrowly collimated jet and the relativistic boosting of its light is what transforms a merely colossal explosion into the brightest singular event we can witness in the entire universe. This leads to a profound and somewhat humbling implication. For every gamma-ray burst we detect, there are hundreds, perhaps even thousands, that we completely miss. Our view of these cosmic cataclysms is not a comprehensive survey. It is a game of chance based on celestial alignment. We only see the burst if our solar system happens to lie within the extremely narrow cone of one of these jets. It's the ultimate cosmic lottery. A star could die in a spectacular gamma-ray burst in a galaxy next door, but if its jets are pointed perpendicular to our line of sight, we will be completely oblivious to the entire event. This means that the brilliant flash we record from the edge of time is not just a testament to the burst's power, but also to a fortunate, or from another perspective, incredibly precise alignment across billions of light years. This lighthouse effect also helps solve a major puzzle in the physics of these events. If the energy of a gamma-ray burst were emitted in all directions, the total energy required to make it visible from such immense distances would be so staggeringly high that it would challenge our understanding of the laws of physics. By concentrating the energy into jets, the total energy budget, while still almost unimaginably large, becomes more consistent with our models of stellar collapse and black hole formation. The jet allows nature to create an illusion of impossible brightness through focus and direction, a natural marvel of physics that enables us to use these events as probes into the farthest reaches of space and time. So, each time a satellite like Swift detects a new burst, it's not just witnessing a random explosion. It's catching a narrowly focused beam of information, a privileged glimpse down the axis of one of the universe's most powerful engines, a view that is granted only through a perfect and fleeting alignment. Among the various ways a star can meet its end, there is one theoretical cataclysm that stands out for its sheer, almost unimaginable violence, a scenario that pushes the limits of stellar physics. This is the pair instability supernova, and its potential connection to the most powerful gamma-ray bursts opens a window into the lives and deaths of the universe's true titans. To understand this phenomenon, we need to venture beyond the familiar realm of core collapse supernova and into the fate of stars so massive that their own light becomes a destructive force. Imagine a star with a mass between 100 and 300 times that of our Sun. In its core, the furnace of nuclear fusion burns at an incredible rate, producing an immense amount of gamma-ray radiation. This radiation exerts an outward pressure that normally supports the star against the inward crush of its own gravity. But in these supermassive stars, the core becomes so hot that the gamma rays themselves, which are pure energy, begin to transform. This is where quantum mechanics takes over in a spectacularly destructive way. When the core temperature soars past 1 billion degrees, the gamma-ray photons become so energetic that they spontaneously convert into pairs of electrons and their antimatter counterparts, positrons. This is the pair instability that gives the explosion its name. Here's the critical part: while photons exert strong outward pressure, these newly created particle pairs exert far less. It's as if the supporting pillars holding up the star's core suddenly vanish. Without that crucial radiation pressure, the star's core can no longer resist gravity. It begins to collapse catastrophically inward, but this is not a collapse that leads to a quiet black hole. Instead, the rapid compression heats the core even further, reigniting runaway nuclear fusion in a titanic thermonuclear explosion. There is no surviving remnant. The entire star is completely obliterated, blasted apart in an explosion so energetic that it can outshine an entire galaxy of normal stars. The amount of radioactive nickel-56 produced in such an event would be colossal, powering a light curve that could shine brilliantly for months. This is not merely a star dying, it is a star committing a form of nuclear suicide, where its own internal physics triggers a total self-annihilation. The connection to gamma-ray bursts, particularly the most distant and energetic ones, is a compelling area of research. A pair instability supernova is, by its nature, an incredibly energetic event. Theoretically, if the progenitor star was also rapidly rotating, the explosion could potentially launch relativistic jets, creating the signature flash of a gamma-ray burst. This makes such stars prime candidates for explaining some of the most luminous and unusual bursts we detect. Specifically, the ultra-long gamma-ray bursts, which shine for thousands of seconds, could be linked to the extended death throes of these supermassive stars. The sheer size of the stellar envelope in a 100 solar mass star would take a relativistic jet much longer to drill through, naturally explaining the prolonged duration of the gamma-ray emission. When we look back to the cosmic dawn, the conditions were perfect for the formation of these stellar behemoths. The first stars, the population 3 stars, are believed to have been predominantly very massive, exactly the kind of factories that could produce pair instability supernova. Therefore, when we detect a particularly energetic or long-lasting gamma-ray burst from a high redshift, we might be witnessing the signature of this rarest of cosmic explosions. It would be a direct observation of a stellar species that no longer exists in the modern, more metal-rich universe, where the presence of heavy elements tends to limit star sizes. The search for the spectroscopic fingerprint of a pair instability supernova in the afterglow of a distant burst is like hunting for a ghost. Astronomers look for specific chemical signatures in the ejected material, such as an unusual abundance of certain elements and a distinct light curve that doesn't match a standard core collapse supernova. While a few candidate events have been identified in the nearby universe, finding one associated with a gamma-ray burst from the edge of time would be a monumental discovery. It would confirm a long-standing theoretical prediction and provide direct evidence for the existence of the first generation of supermassive stars. Each unusually energetic burst from the early universe is therefore a potential message in a bottle, not just from a dying star, but from a star that lived a life of such extreme proportions that its death was a uniquely spectacular event, a final testament to the raw, unbridled power of the infant cosmos. However, this orderly picture of a gamma-ray burst marking the death of a massive star within an identifiable host galaxy is sometimes turned completely upside down. In a puzzling number of cases, once the brilliant afterglow of a burst has completely faded, astronomers point the world's most powerful telescopes toward the precise coordinates, expecting to find the faint, smudgy glow of its home galaxy and see nothing. Just an empty, dark patch of sky. This is the intriguing no-host problem, a mystery that challenges our assumptions and points to some of the more exotic life stories a star can have. It's as if a brilliant firework exploded in the night sky, but when you look for the launch pad, there's nothing there, forcing you to wonder if it was launched from somewhere far beyond the visible horizon. One of the most straightforward explanations for a missing host galaxy is simply the limits of our own technology. We are, after all, trying to detect the faintest objects at the very edge of the observable universe. A galaxy at an extremely high redshift, especially one that is not undergoing intense star formation, might be so intrinsically faint that it falls below the detection threshold of even the Hubble or James Webb Space Telescopes. The gamma ray burst itself, being millions of times brighter than its host for a brief period, acts as a temporary flare, illuminating its location for us. But once that flare dies down, the underlying galaxy may be too dim for our current instruments to see. In these cases, the no-host problem is not a cosmic mystery, but a temporary one, waiting for the next generation of even more powerful telescopes to finally reveal the hidden home. A far more dynamic and compelling explanation involves the idea of a runaway star. Massive stars are not always sedentary citizens of their galactic homes. They can be violently evicted. In the dense, chaotic environments of star clusters, gravitational interactions between stars can act like a slingshot. When two binary star systems pass close to each other, the complex dance of gravity can fling one of the stars outward at tremendous speeds, sometimes hundreds of kilometers per second. Another mechanism involves a star orbiting too close to a supermassive black hole at a galaxy's center, getting a gravitational kick that sends it hurtling into intergalactic space. A star ejected in this way would spend the rest of its life on a solitary journey through the vast, empty darkness between galaxies. If such a runaway star is massive enough to produce a gamma-ray burst, its death would occur far from any galactic light. The resulting burst would appear to have no host because its progenitor star had left its home millions of years before its final cataclysm. The brilliant flash would be a lonely beacon in the void, its light tracing a path that begins not in a galaxy, but in the profound emptiness of the intergalactic medium. This scenario paints a dramatic picture of stellar life and death, a star born in a crowded cluster only to be cast out, living a solitary existence until its spectacular demise illuminates the blackness between islands of stars. The environment of such an explosion would also leave a distinct signature on the burst's afterglow. The intergalactic medium is millions of times less dense than the interstellar medium within a galaxy. When the relativistic jet from a gamma ray burst slams into the surrounding gas, it creates a shock wave that powers the afterglow. If that burst occurs in a near-perfect vacuum, the shock wave has very little material to interact with. This would result in an afterglow that is significantly fainter and fades much more rapidly than one occurring in a typical galactic environment. For some no-host bursts, the unusually quick fade of their afterglow provides strong circumstantial evidence that the explosion did indeed happen in a low-density region, perfectly consistent with the runaway star hypothesis. These ghostly bursts, untethered from any visible galaxy, remind us that the cosmos is not a static picture but a dynamic arena where stars can be born, wander, and die in isolation, their brilliant final acts revealing stories of gravitational upheaval and cosmic exile. Building on the idea of measuring the universe's expansion, gamma-ray bursts are now being pushed into a role that might sound familiar, that of a standard candle. In cosmology, a standard candle is an object with a known, predictable intrinsic brightness. By comparing how bright the object appears to us with how bright we know it actually is, astronomers can calculate its distance with remarkable accuracy. For decades, the premier standard candles have been a specific type of stellar explosion called Type 1, a supernova. These supernovae have a very consistent peak luminosity, making them fantastic cosmic yardsticks that were instrumental in discovering the universe's accelerating expansion. But supernova, even these brilliant ones, have their limits. They simply aren't bright enough to be seen at the extreme distances that gamma-ray bursts can reach. A typical Type 1a supernova might be visible out to a few billion light-years, but a gamma-ray burst from the cosmic dawn is visible from over 13 billion light-years away. If we could somehow calibrate gamma-ray bursts to act as standardizable candles, they would extend our cosmic tape measure right back to the universe's infancy. The key word here is standardizable because unlike Type 1a supernova, which all have nearly identical peak brightnesses, gamma-ray bursts are notoriously diverse. Their energies can vary by a factor of 1,000,000. One burst might be relatively faint, while another could be the single brightest event ever recorded. They come in different durations with different light curve shapes and different spectral properties. Trying to use them as simple standard candles would be like trying to measure distances with a box of light bulbs that included everything from a faint nightlight to a stadium floodlight with no labels on any of them. The challenge, therefore, is not to find a single standard brightness, but to discover a correlation within the burst's observable properties that can tell us what its intrinsic brightness should be. It's about finding a ruler that can adjust its own scale based on the clues the burst provides. This search has led astronomers to identify several promising correlations, often called empirical relations. One of the most studied is the correlation between a burst's luminosity and something called its spectral lag. Spectral lag is a measure of the time delay between the arrival of high-energy gamma rays and lower-energy gamma rays. In simpler terms, in many bursts, the highest energy photons arrive at our detectors a fraction of a second before the lower energy ones. It's a subtle effect, but it turns out to be remarkably informative. Astronomers have found that bursts with a shorter spectral lag, meaning the different energies arrive almost simultaneously, tend to be intrinsically more luminous. Conversely, bursts with a longer lag between the high and low energies are typically less powerful. This gives us a potential calibration tool. By carefully measuring the spectral lag of a newly detected burst, we can make an educated estimate of its true power and from there calculate its distance. Another powerful correlation is between the luminosity of a burst and the peak energy of its spectrum. This is the Amati relation we touched on earlier. More energetic bursts not only release more total energy, but also produce their light at characteristically higher energies. If you can measure the energy at which the burst spectrum peaks, you get a strong hint about its intrinsic luminosity. There are other relations too, like the connection between luminosity and how quickly the light curve varies, suggesting that more rapidly varying bursts are also more powerful. Each of these correlations provides a different, independent way to estimate the burst's true brightness. When multiple relations point to the same answer for a single burst, our confidence in that distance measurement grows significantly. The potential payoff for making this work is enormous. While Type 1a supernova have been brilliant for measuring the relatively recent, accelerating expansion of the universe, they can't probe the first few billion years with the same precision. Gamma-ray bursts, if properly calibrated, could fill this gap. They could allow us to measure the expansion rate of the universe across 90% of cosmic history. This would provide a critical test for our models of dark energy. Is the strength of dark energy constant, as Einstein's cosmological constant suggests, or has it changed over time? By using GRBs to measure distances at redshifts of 2, 4, or even 8, we could see how the expansion rate behaved during eras that are currently poorly sampled, offering new insights into one of the greatest mysteries in physics. However, the path to using GRBs as robust cosmological tools is fraught with challenges. The biggest issue is circularity. To calibrate these empirical relations, to define the exact curve on the graph that connects, say, spectral lag to luminosity, you need a sample of bursts with independently known distances. How do you get those distances? You measure the redshift of the host galaxy from the afterglow's spectrum. But this creates a problem. Your calibration sample is limited to bursts that are bright enough and close enough to have a measurable afterglow and a detectable host galaxy. This might introduce a selection bias where the relations are only accurately defined for a certain type of burst, potentially making them unreliable when applied to the much fainter, more distant events we ultimately want to study. It's a classic chicken and egg scenario that astronomers are working hard to overcome with larger, more carefully selected samples and sophisticated statistical techniques. Despite these hurdles, the progress is promising. Every new gamma-ray burst with a well-measured afterglow and redshift adds a precious data point to the calibration plots, tightening the correlations and reducing the uncertainties. Missions like SWIFT and Fermi have provided the large, uniform datasets needed for this kind of statistical work. The goal is not to replace supernova, but to complement them, creating a multi-messenger distance ladder that reaches from our cosmic backyard to the horizon of the observable universe. Each successful calibration brings us closer to using these titanic explosions not just as fascinating objects of study in their own right, but as fundamental tools for mapping the geometry and history of the cosmos itself, turning the universe's most violent catastrophes into its most far-reaching yardsticks. Now, just as we think we're beginning to understand the most powerful explosion since the Big Bang, the universe presents us with another, even more fleeting and enigmatic signal, the fast radio burst, or FRB. Imagine a gamma-ray burst, but instead of lasting for seconds, its entire energy is released in a blink lasting only a few thousandths of a second. And instead of arriving as the highest energy gamma rays, this flash is concentrated in the radio part of the electromagnetic spectrum, the same kind of waves used for broadcasting and radar. These events are so brief and powerful that for years after their discovery, their very existence was debated. They seemed more like a glitch in the data than a real astrophysical phenomenon. Yet they are real, and their study has opened up a new frontier in time-domain astronomy, one that shares some fascinating, though perhaps superficial, parallels with our quest to understand gamma-ray bursts. On the surface, the differences between these two cosmic transients are profound. A typical long gamma-ray burst is the death cry of a massive star, an event that releases more energy than the Sun will in 10 billion years, and it does so over a comparatively leisurely period of several seconds to a minute. A fast radio burst, in contrast, packs a staggering amount of energy into a pulse that can be as short as a millisecond. To achieve that, the engine behind an FRB must be incredibly efficient and operate on an almost unimaginably short timescale. Furthermore, while we have confidently identified the progenitors of long GRBs, the source of most FRBs remains one of the biggest mysteries in astrophysics. Leading candidates include highly magnetized neutron stars called magnetars, which can experience starquakes that release colossal bursts of energy, or perhaps even more exotic objects. However, where the connection becomes truly intriguing is in the realm of the repeating FRB. While most FRBs, like most GRBs, appear to be one-off cataclysms, astronomers have discovered a small but growing number of sources that erupt multiple times, sending out brilliant radio flashes every now and then. This immediately rules out a destructive origin for these specific bursts. Whatever is producing them must survive the event. This is where a potential link to gamma-ray bursts emerges, not in the common long-duration bursts but in their shorter-lived cousins. The merger of two neutron stars produces a short gamma-ray burst, and it is also theorized to leave behind a remnant, perhaps a hypermassive neutron star that survives for a few milliseconds before collapsing into a black hole or a highly magnetic magnetar. It is conceivable that such a newly formed, unstable object could, in its final moments or in its early life, produce repeated outbursts of radio waves, creating a link between a one-off short GRB and recurring FRB activity. The study of one phenomenon can profoundly inform the study of the other, particularly when it comes to the physics of relativistic plasmas and magnetic fields. Both GRBs and FRBs involve the acceleration of particles to incredible speeds and the generation of intense radiation within powerful magnetic fields. The processes that generate coherent radio emission in an FRB, where waves are emitted in lockstep, making the signal incredibly bright, might share underlying principles with the mechanisms that generate the lower energy end of a GRB's afterglow. By understanding how radiation is produced in one extreme environment, we can develop better models for the other. The techniques honed by gamma-ray burst hunters, the rapid response, the multi-wavelength follow-up, the precise localization have been directly adopted by FRB astronomers. The ability to quickly pinpoint an FRB's location to a specific host galaxy, a feat only recently accomplished, mirrors the pivotal work done by Swift in locating GRB host galaxies, allowing us to understand the cosmic environments that breed these mysterious events. Perhaps the most exciting potential link lies in the possibility of a unified origin for both signals from a single, monumental event. There have been tantalizing, though rare, instances where a high-energy explosion has been associated with a radio burst. In 2020, a magnetar within our own galaxy produced a gigantic flare in X-rays and gamma rays, and simultaneously it emitted an FRB-like radio pulse. This was a landmark discovery, providing the first smoking gun that linked at least some FRBs to magnetar activity. This fuels speculation that a much more powerful magnetar flare in a distant galaxy could potentially produce both a short-duration gamma-ray flash and a cosmological FRB. While a typical long GRB from a collapsar is probably too long and energetically different to be connected to most FRBs, the violent birth of a magnetar in a neutron star merger remains a compelling theoretical bridge between these two classes of cosmic fireworks. Ultimately, both gamma-ray bursts and fast radio bursts serve as extreme laboratories for testing the laws of physics under conditions we can never recreate on Earth. They are both messengers from distant galaxies carrying information about the most energetic processes in the universe. GRBs, as we've seen, illuminate the early universe and the life cycles of massive stars. FRBs, whose radio waves can travel vast distances relatively unimpeded, are now being used as probes to map the otherwise invisible matter distributed between galaxies. By studying the subtle distortion of an FRB signal as it travels to Earth, astronomers can literally weigh the missing baryonic matter in the cosmic web. So, while they may arise from different specific cataclysms, the investigation of both GRBs and FRBs is driven by the same fundamental desire: to understand how the universe unleashes its greatest energies and to use those brilliant flashes to illuminate the dark, empty spaces between the stars. This brings us to a question that often surfaces when we contemplate these titanic explosions from the safety of our living rooms. Could a gamma-ray burst ever pose a threat to life here on Earth? It's a natural thought given the almost unimaginable power we've been discussing. The answer, rooted in both the physics of the bursts and the structure of our galactic neighborhood, is a fascinating blend of sobering possibility and profound reassurance. To understand the risk, we need to imagine a scenario where such a cataclysm unfolds not in a galaxy billions of light-years away, but right in our own cosmic backyard. The mechanism of destruction from a nearby gamma-ray burst would not be a wave of heat or a kinetic impact. Instead, the primary threat would come from radiation. If a long gamma-ray burst were to occur within a few thousand light-years of Earth, and if one of its relativistic jets were pointed directly at us, our planet would be bathed in an intense flash of ultraviolet, X-ray, and gamma-ray radiation. The initial blast would last for less than a minute, but its aftereffects would be catastrophic. The most significant damage would be inflicted upon Earth's ozone layer. This thin shield of gas high in our stratosphere is what protects life on the surface from the sun's harmful ultraviolet radiation. The gamma-ray burst's high-energy photons would break apart the molecules of nitrogen and oxygen in the atmosphere, triggering a cascade of chemical reactions that would produce vast quantities of nitrogen dioxide. This compound acts like a dark brown smog, which would not only help destroy ozone but also blot out a significant amount of sunlight. The consequences would unfold over weeks and months. With the ozone layer severely depleted, lethal levels of ultraviolet radiation from our own sun would reach the planet's surface, causing widespread damage to the DNA of plants and animals. Simultaneously, the nitrogen dioxide haze would lead to a rapid global cooling, potentially triggering a prolonged impact winter or even a snowball Earth scenario, similar to the effects theorized for a large asteroid impact. The combination of radiation poisoning, collapsed food chains due to the loss of photosynthetic plankton and plants, and a deep freeze would almost certainly result in a mass extinction event. Evidence in the geological record has even led some scientists to speculate that a gamma-ray burst might have been responsible for the Ordovician extinction around 450 million years ago, which wiped out a significant portion of marine life. Now for the profound reassurance. While the what-if scenario is terrifying, the probability of it happening is astronomically low for two crucial reasons. First, our Milky Way galaxy is not a fertile breeding ground for the kind of stars that produce long gamma-ray bursts. Remember, these events are linked to the core collapse of massive, rapidly rotating metal-poor stars. Our galaxy is relatively old and metal-rich. The massive stars that do form here today tend to have higher metallicity, meaning they contain more heavy elements. This causes them to lose mass through strong stellar winds during their lives, which slows their rotation. A slower spinning core is far less likely to produce the narrowly collimated jets required for a gamma-ray burst. Instead, these stars are more likely to end their lives in a more common and far less dangerous type of supernova. The galactic environments that are prolific producers of long GRBs are the small, irregular, metal-poor galaxies that were common in the early universe, not grand spirals like the Milky Way. The second, and perhaps even more important, factor is the lighthouse effect we discussed earlier. Even if a rare, unstable star capable of producing a GRB did form somewhere in our galaxy, the threat only exists if we are looking directly down the barrel of its jet. Given that the jets are typically only a few degrees wide, the chance of a randomly oriented burst being aimed at Earth is incredibly small. Statistically, for every GRB whose jet is pointed at us, there are hundreds or even thousands of others whose jets are aimed in other directions, completely harmless to our planet. When you combine the extreme rarity of a suitable progenitor star in our galaxy with the minuscule probability of a favorable jet alignment, the overall risk becomes vanishingly small. Current estimates suggest a galaxy like the Milky Way might experience a gamma-ray burst only once every million years or so, and the odds of one being aimed at Earth over the entire history of our planet are truly infinitesimal. So, while it is a testament to the raw power of the universe that such an event could, in theory, pose a threat from across the galaxy, we can rest easy knowing that our cosmic neighborhood is a remarkably safe haven for life to flourish. This idea that the early universe was a more violent and active place leads us to a fascinating pattern emerging from the data. The rate at which gamma-ray bursts occur is not constant throughout cosmic history. In fact, when we map the detected bursts against their redshifts, a clear trend appears. The further back in time we look, the more frequent these colossal explosions seem to have been. The universe in its youth was a far more dramatic and explosive environment than the relatively sedate cosmos we inhabit today. This isn't just a subtle statistical fluctuation, the difference is profound. During the first few billion years after the Big Bang, the cosmos might have experienced up to 10 times more gamma-ray bursts per unit volume than it does now. This tells us that the conditions for creating these spectacular events were far more common in the past, pointing directly to the nature of the first stars and the evolving chemistry of the universe. A primary driver behind this cosmic boom in gamma-ray burst activity is the very thing that made the early universe so different: its chemical purity. After the Big Bang, the universe was composed almost entirely of hydrogen and helium. It was a metal-free environment, and in astronomy, metals refer to any element heavier than helium. This lack of heavy elements had a direct and dramatic impact on the types of stars that could form. Without metals, the giant clouds of gas that collapsed to form the first stars couldn't cool down efficiently. This inefficient cooling led to the creation of truly monstrous stars, with masses that could reach hundreds of times that of our Sun. These colossal stars, known as population 3 stars, are the ideal progenitors for long-duration gamma-ray bursts. They lived fast, burned hot, and died young in spectacular core collapse supernova that were perfectly set up to produce the relativistic jets we observe as gamma-ray bursts. As the eons passed, the universe underwent a fundamental transformation, a process of chemical enrichment driven by the very explosions we're discussing. Each massive star that died in a supernova or a gamma-ray blast scattered its newly forged heavy elements carbon, oxygen, silicon, iron out into the surrounding gas. Over billions of years, this cosmic recycling program increased the overall metallicity of the universe. This increasing metallicity acted as a brake on the formation of the kind of stars that make gamma-ray bursts. Stars formed from metal-rich gas lose mass much more effectively through powerful stellar winds. This mass loss not only reduces the final mass of the star, but crucially, it also slows down the star's rotation by carrying away angular momentum. A slower spinning core is far less effective at producing the narrow, focused jets required for a gamma-ray burst. So, as the universe aged and became more polluted with heavy elements, the ideal recipe for a gamma-ray burst, a massive, rapidly rotating, metal-poor star, became increasingly difficult to achieve. This evolutionary tale is written in the changing demographics of galaxies. In the modern universe, long gamma-ray bursts are not distributed evenly. They show a strong preference for occurring in small, irregular, and actively star-forming galaxies that have low overall metallicity. These galaxies are, in a sense, cosmic relics, environments that still resemble the conditions of the early universe. In contrast, massive, metal-rich galaxies like our own Milky Way are virtually devoid of gamma-ray burst activity. Our galaxy has all the ingredients for star formation, but the stars it produces today are simply the wrong type. They are born with too many heavy elements to retain the rapid spin and massive structure needed to end their lives as a gamma-ray burst. The declining rate of these explosions over cosmic time is therefore a direct signature of the universe's ongoing chemical evolution, a fading echo of a more chaotic and energetic past. This pattern has profound implications for our understanding of cosmic history. The high rate of gamma-ray bursts in the early universe means that these events were not just rare curiosities, they were a dominant force in shaping their environments. The intense radiation from these bursts would have contributed significantly to the reionization of the universe, helping to burn away the primordial fog of neutral hydrogen. Furthermore, the frequent explosions would have seeded the cosmos with heavy elements at a much faster rate than previously thought, rapidly enriching the gas from which subsequent generations of stars and planets would form. The gamma-ray bursts we detect from the edge of time are not just distant flashes, they are active participants in the story of cosmic evolution, their declining frequency a testament to the fact that their work of building a more complex universe is largely complete. The cosmos has matured, and the age of frequent titanic stellar cataclysms has given way to a quieter era, one where life has had the stable conditions needed to arise and ponder these very explosions. At the heart of this cosmic canon lies one of the most critical and mysterious ingredients, an unimaginably powerful magnetic field. To grasp how a collapsing star can fire a jet of matter to 99.9% the speed of light, we need to move beyond simple explosions and think in terms of a highly organized magnetic engine. The sheer power required isn't generated by a chaotic blast, but by the focused, relentless grip of magnetism operating on a scale we can barely conceive. Within the chaos of the collapsing stellar core, as it funnels down into a newly formed black hole or a hypermassive neutron star, the star's own internal magnetic field gets caught in the whirlpool. This is not the gentle magnetic field of a bar magnet. Think of it as the star's primordial magnetic field being wound up, amplified, and concentrated by the incredibly rapid rotation of the core, like a cosmic dynamo spinning out of control. This process creates a magnetic tower of unbelievable strength. The lines of magnetic force become twisted into a tight coil, channeling the energy of the gravitational collapse along a specific axis. It's this magnetic conduit that acts as the barrel of the gun, collimating and directing the outflow into the two narrow jets we observe. The particles within this jet, electrons and protons, are not simply blasted outward by thermal pressure. Instead, they are slung forward, accelerated by the rotating magnetic field like beads on a tightly wound string that is being whipped around. This mechanism, known as magnetic reconnection, is far more efficient than any explosive shock at transferring energy to particles, allowing them to reach the mind-boggling relativistic speeds that define a gamma-ray burst. Without these ultra-strong magnetic fields, the entire event would be a much messier spherical explosion, lacking the focused beam that makes it visible across the universe. Once this magnetically accelerated jet is launched, the magnetic fields continue to play a starring role in creating the light we actually see. The phenomenon responsible for the brilliant afterglow is called synchrotron radiation. This is a process where high-energy electrons, spiraling at near-light speed along magnetic field lines, are forced to constantly change direction. According to the laws of physics, any charged particle that is accelerated will emit radiation. As these electrons whip around the magnetic fields embedded within the jet, they radiate energy across the electromagnetic spectrum from radio waves up to X-rays. This is the primary source of the sustained glow that follows the initial gamma-ray flash. The entire afterglow, which we so carefully analyze with our telescopes, is essentially a grand display of synchrotron radiation, a cosmic light show powered by electrons dancing in magnetic traps. This intricate sequence of events forms the backbone of the leading theoretical framework, known as the relativistic fireball model. The model begins with the central engine, the black hole or neutron star remnant injecting a tremendous amount of energy into a small volume of space in a very short time. This creates an opaque fireball of radiation and electron-positron pairs, a super-hot plasma that expands relativistically. The model then relies on the magnetic fields to solve a key problem: how to convert the random thermal energy of this expanding fireball into the organized directional motion of a jet and the non-thermal spectrum of the burst we observe. The magnetic fields provide the structure and the acceleration mechanism that shapes the raw power of the collapse into the coherent phenomenon we detect. The observed properties of the light, from the initial gamma-ray pulse to the fading afterglow across different wavelengths, match the predictions of synchrotron emission within this fireball model remarkably well, giving us confidence that we are on the right track to understanding the fundamental physics at play. The significance of these magnetic processes extends far beyond just making the burst bright. The specific characteristics of the synchrotron radiation serve as a direct diagnostic tool for the conditions within the jet. By carefully analyzing the spectrum of the afterglow, how its brightness changes with wavelength, astronomers can actually measure the strength of the magnetic fields and the energy distribution of the electrons millions of light years away. A steeper drop-off in the spectrum indicates a certain ratio of magnetic field energy to particle energy, providing insights into the efficiency of the acceleration process. This allows scientists to peer into the heart of the explosion long after it has faded from view, testing and refining their models of how these universal magnetic engines operate. Each new gamma-ray burst detected adds another data point, helping us understand not just the cataclysm itself, but the fundamental role of magnetism in shaping some of the most energetic events since the beginning of time. For many years, the idea that a gamma-ray burst was the death cry of a massive star remained a compelling but unproven theory. The collapsar model made perfect sense, but the vast distances to most bursts made it impossible to see what was left behind after the brilliant flash faded. The crucial evidence we needed to cement this cosmic connection had to come from much closer to home, from events bright enough and near enough for our telescopes to dissect in fine detail. This evidence arrived in the form of a specific and spectacular class of stellar explosion, the broad line type Ike supernova. Unlike a typical supernova, which expands at thousands of kilometers per second, a type IKBL supernova is characterized by material hurtling outward at velocities approaching a significant fraction of the speed of light. This extreme speed is the first clue, a signature of an explosion that received an extra powerful kick from a hidden engine. The breakthrough came with a handful of fortunate events where a gamma-ray burst occurred in a galaxy close enough for us to get a spectacularly clear view. The most famous of these was GRB 980425, detected in April 1998. This burst was unusually close, originating from a galaxy about 140 million light-years away. As the gamma-ray flash subsided, astronomers witnessed something unprecedented: the gradual rise of a supernova, its light curve peaking days after the initial burst. This was not a coincidence. The timing and location were perfect. The supernova, designated SN 1998 BW, was a textbook broad-line type Ike event. Its spectrum showed the telltale signs of high-velocity ejecta and a distinct lack of hydrogen and helium, indicating the progenitor star had shed its outer layers before its cataclysmic collapse. This was the smoking gun. The gamma-ray burst and the supernova were two parts of the same cosmic event, observed in sequence. The sequence of events paints a complete picture. First, the core of the massive star collapses, forming a black hole and launching the relativistic jets that we see as the brief, intense gamma-ray burst. Moments later, the shock wave from the core collapse rebounds outward, blasting the entire star apart in a tremendous supernova explosion. The two phenomena are intrinsically linked, with the GRB jet acting as the trigger deep within the star and the supernova being the resulting explosion of the stellar envelope. In the case of a type IKBL supernova, the incredible kinetic energy, the sheer speed of the expanding debris, is directly imparted by the same central engine that powered the gamma-ray burst. It's a two-stage cosmic firework. First, a narrowly focused laser-like beam, followed by a colossal spherical detonation. This connection has since been confirmed in several other nearby bursts, such as GRB 030329 and GRB 060218, each time revealing a type IKBL supernova emerging from the afterglow. These observations have solidified the collapsar model as the standard explanation for long-duration gamma-ray bursts. They prove that these are not isolated jets in empty space. They are the final, violent acts of stars that were born massive, lived fast, and died young, leaving behind both a brilliant beacon and an expanding cloud of newly forged elements. The supernova is the star's final farewell to the universe, while the gamma-ray burst is its ultra-focused last will and testament, a message inscribed in the highest energy light imaginable. While we can study the light and radiation from these distant explosions, that information has traveled for billions of years, interacting with gas and dust along the way. To truly understand the engine at the heart of a gamma-ray burst, we need a messenger that can travel directly from the source, unaffected by anything in its path. This brings us to the hunt for one of the most elusive particles in the universe, the neutrino. Neutrinos are fundamental particles with almost no mass and no electric charge, which makes them cosmic ghosts. They can pass through entire planets as if they weren't even there. This same property that makes them so difficult to detect also makes them perfect messengers. If a neutrino could be created in the central engine of a gamma-ray burst, it could race across the universe in a perfectly straight line, carrying an uncontaminated sample of information about the conditions of its birth, arriving at Earth just moments after the initial gamma-ray flash. The theoretical case for neutrino production in a gamma-ray burst is incredibly strong. Within the relativistic jet, protons are accelerated to tremendous energies. These protons can collide with the intense radiation field also present in the jet, a process known as the photomeson interaction. In these collisions, subatomic particles called pions are created. These pions are unstable and rapidly decay, and one of the primary decay products is a muon neutrino. This entire chain of events would happen in the first few seconds of the burst's life, deep within the maelstrom surrounding the newborn black hole. The resulting neutrinos would be incredibly energetic, carrying millions or even billions of times more energy than those produced by our Sun or in nuclear reactors on Earth. These high-energy neutrinos are the specific quarry for astronomers, as their detection would be a direct confirmation of the hadronic processes, the acceleration of protons within the jet, something that observations of light alone can only infer indirectly. The monumental challenge, of course, is catching these ghostly particles. This is the mission of observatories like IceCube, a spectacular instrument buried deep in the Antarctic ice at the South Pole. IceCube isn't a traditional telescope with mirrors and lenses. It is a colossal detector consisting of over 5,000 optical sensors embedded in a cubic kilometer of pristine ice between 1 and 2 kilometers below the surface. This immense volume of ice acts as a target. On the incredibly rare occasion that a high-energy neutrino passing through the Earth does interact with an atom in the ice, it produces a secondary particle called a muon. This muon, traveling faster than the speed of light in ice, creates a faint flash of blue light known as Cherenkov radiation. The string of sensors captures this fleeting light, allowing physicists to reconstruct the direction and energy of the original neutrino with remarkable precision. The search strategy is a sophisticated game of cosmic timing. When a satellite like Swift or Fermi detects a gamma-ray burst, it instantly sends out an alert with the precise time and location of the event. The IceCube team then searches their data for any neutrino candidates that arrived from that same patch of sky within a specific time window around the burst. This is a needle in a haystack search of the highest order, as neutrinos from all over the universe are constantly raining down on Earth. The goal is to find a statistically significant excess of neutrinos that cannot be explained by random background fluctuations. A single high-confidence correlation between a neutrino and a specific gamma-ray burst would be a landmark discovery in multi-messenger astronomy, opening an entirely new window onto the most powerful explosions in the universe. So far, despite years of searching and analyzing data from hundreds of gamma-ray bursts, a definitive neutrino signal has remained elusive. This non-detection is in itself a profound scientific result. It tells us that perhaps the jets in gamma-ray bursts are not as efficient at accelerating protons as some theories predicted. It might imply that the energy in the jet is dominated by the acceleration of electrons, which produce the synchrotron radiation we see rather than protons. Alternatively, it could indicate that the conditions within the jet, the density of radiation or the strength of the magnetic fields, are not quite right for the efficient production of pions. Each null result helps physicists refine their models, tightening the constraints on how these cosmic engines actually operate. The hunt is far from over. Next-generation neutrino telescopes are being planned, with even larger volumes to increase the chance of a detection. The pursuit of a neutrino from a distant gamma-ray burst represents a fundamental step in our quest to understand the universe. It moves us from passively observing the light from these cataclysms to actively seeking out a particle that was forged in the explosion itself. A successful detection would do more than just confirm a theory. It would allow us to literally see inside the engine, measuring its power and composition in a way that light alone can never allow. It would transform these brilliant beacons from the edge of time into true multi-messenger events, their stories told not just by photons but by the ghosts of the cosmic abyss. But for all the cosmic fireworks we've been discussing, there exists a mysterious class of these explosions that seem to vanish without a trace, events that defy our expectations and highlight the challenges of observing the distant universe. These are the so-called dark gamma-ray bursts. The scenario is a familiar one for astronomers. A satellite like Swift detects the brilliant flash of gamma rays, pinpoints its location with precision, and alerts telescopes around the world. They swing into action, searching for the predictable, fading afterglow in visible light. Yet, in a significant number of cases, they find nothing. The spot in the sky where the cataclysm occurred remains stubbornly dark to optical telescopes. It's as if a massive star died, sent out a final, powerful scream in the highest energy light, and then simply disappeared into the void. The mystery of these dark bursts isn't that the explosion failed to produce an afterglow. The physics of the relativistic jet slamming into interstellar gas is too robust for that. The afterglow is almost certainly there, but something is blocking our view. The most common culprit is a cosmic one: dust. Galaxies, especially those that are actively forming stars, are filled with vast clouds of microscopic dust grains composed of carbon and silicon, forged in the hearts of previous generations of stars. When the brilliant bluish light of a gamma ray burst's afterglow tries to pass through these dense clouds, the dust acts like a thick fog, absorbing and scattering the shorter wavelengths of visible light. What little light makes it through is significantly reddened and dimmed, often to the point where it falls below the detection limit of even our most powerful optical telescopes. A burst that occurs in an extremely dusty galaxy can therefore be rendered effectively invisible in the part of the spectrum we most commonly use to study it. This is where the incredible distance of a burst becomes a critical factor, intertwining with the dust extinction effect in a fascinating way. Remember the phenomenon of cosmological redshift. The expansion of the universe stretches the wavelength of light as it travels. For a gamma ray burst from the cosmic dawn, this stretching is so extreme that the entire visible light portion of its afterglow is shifted far into the infrared part of the electromagnetic spectrum. So, even if there were no dust at all in the host galaxy, a very high redshift burst would naturally appear dark to a standard optical telescope because the light it emitted as visible wavelengths has been transformed into infrared light by the time it reaches us. It's not missing, it's just been moved to a color our eyes cannot see. Now, combine these two effects. Imagine a gamma-ray burst occurring in a primitive, dust-filled galaxy at the edge of the observable universe. The afterglow light is both intrinsically redshifted into the infrared and further dimmed and reddened by the intervening dust in its own galaxy. This double whammy makes these events exceptionally difficult to detect with traditional methods. For years, these dark bursts represented a significant gap in our understanding, a selection bias that meant we were potentially missing a whole population of explosions that occurred in the most heavily obscured and perhaps most actively star-forming environments in the early universe. The solution to this puzzle has arrived with the advanced capabilities of the James Webb Space Telescope. Webb is uniquely equipped to solve the mystery of dark gamma-ray bursts because its entire design is optimized for infrared astronomy. Its sensitive instruments are not fooled by the dust extinction that blocks optical light, and they are perfectly tuned to capture the deeply redshifted light from the most distant events. When a satellite detects a potential dark burst, Webb can now point its massive mirror toward the location and search for the afterglow in the infrared, where the light has both naturally migrated and where dust is more transparent. In many cases, what was dark to Hubble is brilliantly clear to Webb. This allows astronomers to finally measure the redshift of these elusive events and study their host galaxies, revealing that they are often incredibly dusty, compact starburst galaxies, rapidly building themselves up through intense episodes of star formation. The dark gamma-ray burst phenomenon, therefore, is not a failure of the explosion but a signature of its environment. And with new tools, we are now bringing these hidden cosmic cataclysms out of the shadows and into the light of our understanding. Now we venture into a realm where the very fabric of spacetime itself leaves a distinct fingerprint on the signals we receive, a subtle but crucial effect known as time dilation. To grasp this, let's start with a simple analogy. Imagine two identical clocks, one here on Earth and one on a spaceship traveling away from us at an incredible speed. Due to the effects of special relativity, we would see the clock on the moving spaceship tick more slowly than our own. The expansion of the universe produces a similar, though more complex, effect on the light from distant galaxies. Because space itself is stretching, a distant gamma-ray burst is effectively moving away from us at a tremendous velocity. This causes the observed passage of time for the entire event to be stretched out, like a recording being played back at a slightly slower speed. This means the duration of a gamma-ray burst that we measure here on Earth is not its true, intrinsic duration. A burst that actually lasted for only 10 seconds in its own rest frame right next to the exploding star will appear to us to last significantly longer. The amount of this stretching is directly tied to the burst's redshift. For a burst at a redshift of 1, which corresponds to a time when the universe was about half its current age, the time dilation factor is about 2. That 10-second burst would be observed as a 20-second-long event. But for a truly distant burst from the cosmic dawn, like one at a redshift of 8, the effect is far more dramatic. The time dilation factor is a staggering 9, meaning that same 10-second explosion would play out over a minute and a half from our perspective. We are watching the cataclysm in extreme slow motion, the expansion of the universe itself acting as a cosmic drag on the perceived pace of the event. This has a profound and very practical implication for one of the most basic classifications in gamma-ray burst astronomy, the split between long and short bursts. You'll recall that this division is fundamental, separating the death of massive stars from the mergers of neutron stars with the dividing line set at 2 seconds. But this classification is based on bursts we observe in our local universe, where time dilation is negligible. When we look to the edge of the observable universe, that 2-second rule can no longer be applied naively. A short burst from a neutron star merger, which might have an intrinsic duration of only half a second, could be stretched by time dilation to appear several seconds long when it arrives from a high redshift. To our satellites, it could masquerade as a long-duration burst, completely misleading us about its true origin. Therefore, astronomers must perform a crucial correction. After measuring a burst's redshift from its afterglow, they can calculate the time dilation factor and mathematically dilate the observed light curve, compressing it back to its original timescale. This allows them to determine the burst's intrinsic duration and correctly classify it. This process has confirmed that the most distant gamma-ray bursts are indeed almost exclusively long-duration events, as expected from the collapse of the first massive stars. It has also helped identify a few potential short bursts at moderate redshifts, proving that neutron star mergers were occurring billions of years ago. This careful accounting for relativity is essential. Without it, our census of stellar deaths throughout cosmic history would be fundamentally distorted, like trying to understand the lifespan of different animal species by watching them through a funhouse mirror that unpredictably stretches time itself. While satellites like Swift and Fermi are our indispensable sentinels in space, Their crucial alerts are only the starting pistol for a coordinated global race that takes place right here on Earth. The moment a gamma-ray burst is detected, an automated signal is beamed down to a worldwide network of robotic observatories, triggering a carefully orchestrated scramble that operates with a speed and precision that would be impossible for human operators alone. These are not the iconic domes housing massive telescopes that require an astronomer to be physically present. These are fully autonomous instruments, pre-programmed to spring into action at a moment's notice, their sole purpose to capture a fading cosmic ember before it vanishes forever. This rapid response ground game is what transforms a fleeting satellite detection into a profound cosmological measurement. The need for this speed is dictated by the brutal physics of the afterglow itself. In the first few minutes after the initial gamma-ray flash, the optical afterglow is at its absolute brightest. It is a brilliant, hot point of light that then begins to fade rapidly, its intensity dropping exponentially with every passing second. Capturing this early, bright phase is not a matter of convenience. It is the fundamental requirement for securing a redshift measurement. To measure a redshift, astronomers need to spread the afterglow's light into a detailed spectrum, a rainbow of colors that contains the dark absorption lines acting as a cosmic barcode. A faint afterglow simply doesn't provide enough photons to create a clear, high-quality spectrum. It's the difference between trying to read a book under a bright reading lamp versus a single dying candle. The robotic telescopes are designed to catch the light while the reading lamp is still on. Consider the process a typical robotic telescope follows. Situated at a premier observing site, like the Roque de los Muchachos Observatory in the Canary Islands or the Cerro Tololo Inter-American Observatory in Chile, the telescope sits idle until a high-priority alert flashes across its control system. Within seconds, complex software calculates the object's current position in the sky, accounting for the Earth's rotation. The dome opens and the telescope slews a smooth, rapid movement to point directly at the coordinates. It often begins by taking a quick series of images through different colored filters to confirm the afterglow's position and measure its initial brightness. But the real prize is the spectrum. The telescope's arm will then swing a spectrograph into place, and for the next precious 5, 10, or 20 minutes, it will collect the faint stream of photons, dispersing them to reveal their hidden secrets. All of this happens without a single human command, a testament to the automation that defines modern astronomy. The data collected in this narrow window is irreplaceable. That early spectrum provides the cleanest possible snapshot of the afterglow's intrinsic properties before it becomes contaminated by the light of the underlying host galaxy or distorted by its own rapid evolution. It allows for the most accurate measurement of the redshift, the number that anchors the entire event in space and time. Furthermore, the very shape of the light curve in those first minutes, how quickly the light fades, holds vital clues about the structure of the jet and the density of the environment surrounding the exploded star. A very rapid fade might indicate the jet is plowing into a particularly low-density region of space, while a slower decline could suggest a denser environment rich with stellar wind material. This rapid response data is the foundational layer upon which all subsequent, more detailed observations are built. This global network is a triumph of international collaboration. When a burst is detected, the alert is sent to dozens of robotic telescopes scattered across the globe, ensuring that regardless of the time of day or which hemisphere the burst occurs in, at least one facility will be in darkness and ready to observe. Telescopes with names like the Liverpool Telescope, the Master Network, and the Zadko Telescope work in concert, sometimes passing the baton from one to the next as the Earth turns, allowing for continuous monitoring of the afterglow's fade. Their success has been instrumental in building the catalog of high redshift gamma-ray bursts that now allows us to probe the era of the first stars. Without these swift, unmanned sentinels on the ground, the brilliant flashes from the cosmic dawn would remain enigmatic blips on a satellite's detector. their profound messages from the edge of time forever lost to the darkness. The incredibly detailed spectrum of a gamma-ray burst's afterglow does more than just give us a single distance measurement. It acts as a core sample through billions of years of cosmic evolution, revealing a complex structure that astronomers poetically call the Lyman alpha forest. To understand this, picture the journey of the burst's light not as a trip through empty space, but as a voyage through a vast cosmic web. Stretching between galaxies are enormous filaments and clouds of primordial gas, mostly neutral hydrogen. As the brilliant beam of the afterglow travels toward us, it passes through this intricate network. Each cloud of hydrogen it encounters acts like a filter, absorbing a very specific wavelength of ultraviolet light associated with the Lyman alpha transition of the hydrogen atom. Because the universe is expanding, each cloud is at a slightly different distance, and thus moving away from us at a different speed. This means the specific wavelength of light absorbed by each cloud gets redshifted by a unique amount. The result is not one single absorption line, but a whole series of them, a veritable forest of dark lines etched into the afterglow's spectrum at different redshifts, each line representing a different cloud of gas encountered along the path. The density of this forest is a direct probe of the era from which the burst originates. For a gamma-ray burst happening in the local universe, the Lyman alpha forest is relatively sparse. The clouds are there, but the vast bubbles of ionized gas blown by billions of years of stellar activity have cleared out much of the intervening neutral hydrogen. However, when we analyze the spectrum of a burst from the cosmic dawn, the forest becomes incredibly thick and dense. This is because we are looking back to a time before the universe was fully ionized, when the cosmic web was still filled with a pervasive fog of neutral hydrogen. The light from a high redshift burst has to pass through this dense, primordial medium, resulting in a spectrum that is almost completely carved up by absorption lines. It's the difference between looking at a distant mountain through a clear summer sky versus seeing it through a dense, patchy fog. The view from the early universe is obscured by the very material that had not yet been burned away by the first stars and galaxies. This makes the Lyman alpha forest from a distant gamma-ray burst one of the most powerful tools available for mapping the large-scale structure of the early universe. Each absorption line is like a pin on a cosmic map, marking the location of a specific cloud of gas. By analyzing the pattern and redshift of these lines, astronomers can reconstruct the distribution of matter along that particular line of sight. They can measure the sizes and densities of these ancient gas clouds and even study how they cluster together, revealing the skeleton of the cosmic web as it existed billions of years ago. Since gamma-ray bursts can be detected from much greater distances than ordinary galaxies, they provide these incredibly long sight lines through the cosmos, allowing us to sample the universe's structure across vast stretches of space and time that would otherwise remain invisible. Furthermore, the properties of the forest hold crucial information about the Epoch of Reionization itself. The very deepest, most redshifted absorption lines in the forest come from the gas clouds closest to the burst, existing at nearly the same early time. If the burst occurred while the universe was still largely neutral, the forest will extend right up to the burst's own redshift with very little gap, a signature of a still opaque cosmos. If the burst went off after reionization was mostly complete, there will be a noticeable clearing, a region in the spectrum closer to the burst where the absorption lines become much weaker or disappear altogether, indicating that the fog had been lifted in that part of the universe. Each high redshift gamma-ray burst spectrum is therefore a unique fossil record, its Lyman alpha forest encoding a detailed history of the ionization state of the intergalactic medium, allowing us to chart the progress of this fundamental cosmic transition one brilliant flash at a time. While gamma-ray bursts are rightly famed for their destructive power, capable of sterilizing planets and shredding nearby gas clouds, there is a fascinating and counterintuitive possibility that these same cataclysms might also be agents of creation. Beyond the immediate zone of annihilation, the colossal shockwave from a GRB can act as a cosmic sculptor, compressing vast clouds of gas and dust in a way that might actually trigger the birth of new stars. It's a profound concept of cosmic feedback where a stellar death gives rise to new stellar life, a cycle of destruction and creation playing out on a galactic scale. The mechanism for this lies in the physics of shock waves traveling through the interstellar medium. When the relativistic jet from a gamma ray burst slams into the surrounding gas, it doesn't just heat it, it creates a powerful, expanding shell of material, much like a spherical snowplow pushing everything in its path. This shell, traveling at supersonic speeds, sweeps up the tenuous interstellar gas, gathering it into an increasingly dense and massive wall. As this wall of gas collides with other pre-existing clouds or with itself as it expands, the resulting pressures can become immense. Under these extreme conditions, the delicate balance within a stable gas cloud can be upset. The increased pressure can overcome the cloud's internal support mechanisms like thermal pressure or magnetic fields, causing it to gravitationally collapse. This collapse is the very first step in the formation of a new star. In essence, the GRB's shockwave gives the cloud a violent push over the cliff of gravitational instability. This idea becomes especially compelling when we consider the environment of the early universe. During the cosmic dawn, galaxies were much smaller, denser, and packed with vast reservoirs of pristine hydrogen and helium gas. A gamma ray burst occurring in such a compact, gas-rich environment would have a far more dramatic impact than one in today's more spread out and evacuated galactic disks. The shockwave wouldn't have to travel far to encounter another massive cloud of star-forming fuel. In these primordial galaxies, a single GRB could have initiated a chain reaction. The initial burst triggers the collapse of a nearby cloud, leading to the formation of new massive stars. Those new stars would then live their short lives, and if they were also massive enough, potentially die in their own gamma-ray bursts, sending out new shockwaves to trigger yet another round of star formation. This propagating wave of creation could have been a significant mechanism for rapidly building up the stellar content of the first galaxies. Astronomers look for evidence of this process by studying the neighborhoods of nearby gamma-ray bursts and supernova. In several cases, they have observed what are called superbubbles, large, hollowed-out regions of gas surrounded by a dense shell of material. These structures are often sites of vigorous ongoing star formation along their edges, suggesting that a previous generation of massive stars, through their winds and ultimate explosions, carved out the cavity and triggered the new wave of star birth. While directly observing this chain of events for a specific gamma-ray burst in a distant galaxy is incredibly challenging, these local analogs provide strong support for the underlying physics. The tremendous energy injected into space by stellar cataclysms doesn't just vanish. It rearranges the galactic landscape and, in doing so, can set the stage for the next act in the cosmic drama of stellar life and death. This journey to the edge of observation inevitably leads us to a profound and fundamental barrier, a horizon beyond which even the most powerful explosions cannot be seen. We are contemplating the absolute limit of how far back in time a gamma-ray burst can possibly take us. This limit is not set by our technology, but by the very history of the universe itself. It is defined by the end of the cosmic dark ages, that mysterious period following the Big Bang when the cosmos was a vast, dark, and starless void. Before this epoch, there were no stars and therefore no massive stars to collapse and produce gamma-ray bursts. A flash of light from this era is a physical impossibility, a contradiction in terms. The ultimate discovery, then, would be a gamma-ray burst from the very first generation of stars, a signal from the moment the darkness was first broken. The cosmic dark ages began about 380,000 years after the Big Bang, after the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. This transition rendered the cosmos transparent but also utterly dark. With no stars to light it up, the universe was filled with a featureless, pervasive fog of this primordial gas. This era lasted for several 100 million years, a long, quiet chapter in cosmic history. The darkness only began to lift when gravity slowly pulled the first clumps of hydrogen and helium together, eventually creating densities high enough to ignite nuclear fusion. The ignition of that very first star, often called a population 3 star, marked the cosmic dawn and the end of the Dark Ages. The period that followed, known as the Epoch of Reionization, was when these first stars and galaxies began to flood the universe with ultraviolet light, slowly burning away the neutral hydrogen fog. Therefore, the earliest possible gamma-ray burst we could ever hope to detect would be one from that initial wave of stellar formation. It would be the death cry of one of the very first stars to ever exist. The theoretical redshift for such an event would be staggering, somewhere around Z equals 20 or even higher, corresponding to a time when the universe was only 200 million years old. Detecting a burst from this frontier would be the astronomical equivalent of finding a fossil of the very first creature to walk on land. It would provide a direct glimpse into the conditions that existed at a pivotal moment of transformation. It would tell us about the mass, the environment, and the death throes of the pioneers that ended the cosmic night. Yet, this ultimate discovery remains tantalizingly out of reach, likely sitting just beyond the current capabilities of our greatest observatories. The challenge is immense. First, the light from such an event would be stretched by cosmological redshift to such an extreme degree that its afterglow would peak in the far infrared or even sub-millimeter part of the spectrum, wavelengths that are incredibly difficult to observe with high sensitivity. Second, the universe at that time was still largely filled with neutral hydrogen, which would absorb a significant portion of the afterglow's ultraviolet and blue light, creating a deep-gun Peterson trough that could make the signal exceptionally faint. Finally, there is the simple statistical reality. The first stars were likely spread far apart, and the rate of gamma-ray bursts per unit volume, while higher than today, was still very low. We are searching for a needle in a haystack of truly cosmic proportions. This observational horizon represents the final frontier for gamma-ray burst astronomy. Pushing beyond it will require a new generation of telescopes both in space and on the ground, designed specifically to probe these deepest of depths. The James Webb Space Telescope has already begun to reveal galaxies from this era, but detecting the fleeting, point-like flash of a gamma-ray burst from within them is a much greater challenge. Future missions concept, like the proposed Lynx X-ray Observatory or Advanced Radio Telescope arrays, might possess the sensitivity and rapid response capabilities needed to catch these primordial explosions. The hunt for a gamma-ray burst from the cosmic dawn is more than a quest for a record. It is a drive to witness the very first stellar deaths, the events that began the process of transforming a simple, dark universe into the complex, luminous cosmos we call home today. Until then, this limit stands as a silent reminder of the final, unobserved chapter in the story of the first stars. But for all the sophisticated satellites and giant telescopes operated by professional astronomers, there's another, increasingly vital force contributing to our understanding of these cosmic explosions: the global community of citizen scientists. This collaborative spirit is beautifully embodied in projects like the Gamma-Ray Burst SkyMap, where amateur astronomers with their own backyard telescopes can play a crucial role in the real-time chase to capture a fading afterglow. It's a powerful reminder that in the 21st century, cutting-edge astrophysics isn't just the domain of large institutions. It's a truly collective human endeavor, connecting enthusiasts around the world to the farthest reaches of the cosmos. The process begins the moment a satellite like Swift sends out its automated alert. These alerts are public, flowing into online databases and specialized apps that anyone can monitor. A project like Gamma-Ray Burst SkyMap acts as a central hub, translating the raw celestial coordinates into an accessible map and providing clear instructions for observers. An amateur astronomer, perhaps in their garden in Germany or on a rooftop in Chile, receives a notification on their phone. They see that a burst has just gone off in a constellation that's currently above their horizon. The race is on. They rush to their telescope, an instrument that, while smaller than a professional observatory's, is often equipped with highly sensitive digital cameras and sophisticated computer controls. They input the coordinates, and their telescope automatically slews to the precise patch of sky, beginning a series of exposures to hunt for the new point of light that wasn't there the night before. The data these dedicated individuals collect is far from just a pretty picture. For a gamma-ray burst with a long-lasting afterglow, professional observatories often cannot justify spending night after night monitoring a single target. Their time is incredibly precious and scheduled months in advance. This is where the global network of amateurs becomes indispensable. They can provide continuous coverage, taking measurements of the afterglow's brightness over many hours, days, or even weeks. This produces a detailed and extensive light curve that shows exactly how the object is fading. A smooth, predictable decay tells one story, perhaps of a jet expanding into a uniform medium. A sudden bump or a plateau in the light curve, however, can signal something more complex, like the jet interacting with a shell of material ejected by the star before its death or the emergence of an underlying supernova. These subtle features are gold mines for theorists, and they can only be caught with sustained, patient observation. This contribution extends beyond just the bright, well-behaved afterglows. They are particularly valuable for following up on the enigmatic dark gamma-ray bursts. If a large professional telescope fails to find an optical afterglow, amateurs can conduct deep searches, using their flexibility to take very long exposures. Even a non-detection is valuable scientific data, as it places an upper limit on the brightness of the afterglow, supporting the hypothesis that the burst is either extremely distant or heavily obscured by dust. Furthermore, in the critical first hour after a burst, while a large telescope might still be slewing into position or waiting for the sun to set at its location, an amateur on the other side of the planet might already be collecting the first precious data points on the afterglow's rise and peak, a phase that is often missed but holds vital clues about the initial physics of the explosion. This model of distributed science represents a fundamental shift in how we explore the universe. It leverages the passion, skill, and geographical distribution of thousands of individuals, creating a responsive, 24/7 monitoring network that no single observatory could ever match. For the participants, the reward is the profound thrill of knowing that the data from their personal telescope, uploaded to a shared database, will become part of a scientific paper, contributing to our collective understanding of black holes, stellar death, and the early universe. It transforms the experience of stargazing from a solitary hobby into an active partnership in discovery, proving that the light from a dying star 13 billion light-years away can connect not just with a satellite in orbit, but with a curious human being in their own backyard, bridging the vastness of space with the power of shared curiosity. Now, to truly appreciate the raw power of these cosmic engines, we need to tackle one of the most important and often misunderstood concepts in gamma-ray burst physics: the difference between isotropic energy and the true collimated energy. When a satellite measures the total amount of energy received from a distant burst, it's a bit like standing across a dark field from someone who flashes a laser pointer directly at your eyes. For that brilliant, fleeting moment, it seems impossibly bright. If you were to naively assume that laser pointer was actually a light bulb shining equally in all directions, you would vastly overestimate its total power output. This is precisely the distinction astronomers have to make. The isotropic equivalent energy is that initial, naive calculation. It's the amount of energy the burst would have released if it were a simple, spherical explosion, radiating its power uniformly across the entire sky. It's a useful first step because it's easy to calculate from the observed brightness and the distance, but it's almost certainly not the real story. The real story, as we've learned, is beaming. The energy is not spread out in a sphere, it is concentrated into those incredibly narrow opposing jets. This is the collimated energy. The difference between the two figures is not a small correction, it can be staggering. For a typical long gamma-ray burst, the jet might only be 5 or 10 degrees wide. Because the area of a sphere is so large, confining the same apparent brightness into such a small solid angle means the true energy required is thousands of times smaller than the isotropic equivalent value. A burst that appears to release a staggering 10 to the 54 ergs of energy, more than the Sun will emit in its entire 10 billion-year lifetime, might actually be powered by an engine that output a mere 10 to the 51 ergs when we account for the focusing of the jet. This correction is not just a minor accounting detail, it's absolutely crucial for understanding what is physically possible within the laws of physics. Why does this matter so much? Because the isotropic equivalent energy of the most powerful bursts pushes against the very limits of what we think is physically possible for a stellar collapse. If that energy were truly emitted in all directions, it would require mechanisms that border on the fantastical, perhaps involving energies that challenge our understanding of relativity and particle physics. However, when we apply the beaming correction, the energy budget suddenly becomes much more reasonable, fitting comfortably within the theoretical framework of a collapsing massive star forming a black hole and an accretion disk. This correction allows us to reconcile these phenomenal cosmic fireworks with known astrophysical processes. It tells us that nature isn't breaking the rules, it's just using a very clever trick with optics and relativity to create an illusion of impossible brightness. This understanding also helps solve a long-standing puzzle about the remnants of gamma-ray bursts. If the explosion were truly spherical and as energetic as the isotropic calculation suggests, the surrounding interstellar medium would be scoured away for light years in every direction, leaving a vast, empty cavity. Yet, observations of nearby burst sites often show a more complex and less devastated environment. When we model the impact of a narrowly focused jet, the damage is far more localized. The jet drills a hole through the star and then interacts with a much smaller volume of space, creating a pattern of destruction that aligns much better with what we actually see. This correction for beaming, therefore, connects the theoretical models directly to the observational evidence, creating a consistent and coherent picture of how these stellar cataclysms actually unfold and interact with their galactic surroundings. The fading light of a gamma-ray burst's afterglow holds a secret language, and one of its most important dialects is revealed not in its overall dimming, but in how it dims across the rainbow of colors. This phenomenon, known as a chromatic break, is a crucial piece of the puzzle for astronomers trying to reconstruct the exact nature of the explosion. The term chromatic simply means related to color, and a break refers to a distinct change in the rate at which the light fades. What we observe is that the afterglow doesn't fade uniformly. The blue light might dim very rapidly after a certain point, while the red light continues to fade at a more gradual pace. This divergence in behavior is not a random glitch. It's a direct consequence of the physics happening within the expanding shockwave and the structure of the jet itself. To understand why this happens, we need to revisit the engine of the afterglow, the relativistic shock wave. As the jet plows into the surrounding interstellar gas, it creates a forward shock that accelerates electrons to nearly the speed of light. These electrons then spiral around magnetic field lines, emitting synchrotron radiation across the spectrum, from radio waves up to X-rays. However, the efficiency of this radiation depends on the energy of the electrons. Higher energy electrons, which produce higher energy light like X-rays and blue visible light, lose their energy much more quickly than lower energy electrons, which produce radio waves and red light. This fundamental difference sets the stage for the chromatic break. Initially, in a freshly energized shock, both high and low energy electrons are abundant, and the afterglow fades at a similar rate in all colors. But as time passes, the highest energy electrons get depleted first. The critical moment, the chromatic break, occurs when a specific physical change sweeps through the jet. One of the most common causes is when the jet, which is initially expanding at ultra-relativistic speeds, begins to slow down significantly as it accumulates more and more mass from the interstellar medium. When this deceleration happens, the rate at which new electrons are accelerated to the highest energies drops dramatically. The supply of blue light producing electrons is effectively cut off, causing the blue component of the afterglow to suddenly steepen its decline. The red light, produced by more resilient, lower energy electrons, is less affected and continues its more sedate fade. The exact timing of this break in the light curve tells astronomers the precise moment the jet has swept up enough mass to slow down to a specific threshold, which in turn allows them to calculate the density of the surrounding environment. A very early break suggests the jet is plowing into a dense region, like the stellar wind from the progenitor star, while a late break points to a very low-density environment. Another scenario that produces a chromatic break involves the geometry of the jet itself. Relativistic jets are not simple pencils of light. They have a structure, often with a very energetic core and less energetic material around the edges. As the jet expands and decelerates, an effect called relativistic beaming changes. Initially, we only see the bright on-axis core of the jet, but as it slows, the beaming angle widens and we suddenly start to see the fainter off-axis material. This off-axis material emits its light at characteristically lower frequencies. So, when this transition happens, there is a noticeable break where the high energy emission from the core fades rapidly, but the lower energy emission from the jet's wings becomes more prominent, slowing the overall fade at those redder wavelengths. By meticulously measuring the properties of these chromatic breaks across the entire spectrum, from radio to X-rays, astronomers can perform a kind of cosmic tomography, reconstructing the jet's energy profile, its opening angle, and the precise density of the gas it's traveling through, turning a simple fading light into a detailed blueprint of the explosion's aftermath. This journey to the absolute edge of the observable universe, to the depths of the very first stars, brings us to a theoretical frontier that is even more profound. What if the first sources of light in the cosmos weren't stars at all, but something far more exotic? We now venture into the realm of speculation, to the possibility of gamma-ray bursts that stem not from stellar death, but from stellar birth of the most extreme kind. The direct collapse of primordial gas clouds into massive black holes. This process would bypass the star-forming stage entirely, creating a black hole seed so colossal it could help explain how supermassive black holes appeared so early in the universe's history. The signature of such an event would be unlike anything we have ever seen, representing a completely new class of cosmic cataclysm. To understand this, we must rewind the cosmic clock to a time before the first stars during the deep cosmic dark ages. The universe was filled with pristine hydrogen and helium gas, slowly cooling and condensing under its own gravity. The prevailing theory is that this gas eventually fragmented into clumps that became the first population 3 stars. However, under very specific conditions, this fragmentation might have been suppressed. In regions of space that were exceptionally dense and bathed in a strong background of Lyman-Werner radiation, a specific type of ultraviolet light that can prevent hydrogen molecules from forming, the gas cloud could have avoided splitting into smaller pieces. Instead of forming many small stars, the entire giant cloud, containing the mass of 100,000 suns or more, would have begun a monolithic, direct collapse. This collapse would not be a gentle process. Without the stabilizing pressure of nuclear fusion at its core to hold it up, the gas cloud would have fallen inward unimpeded, accelerating to incredible speeds. The friction and collisions within this inrushing river of gas would have heated it to immense temperatures, causing it to glow brilliantly, not as a star but as a superheated accretion flow. At the very center, the density and gravity would become so overwhelming that a singularity would form, a black hole but not one of stellar mass. This would be a direct collapse black hole, born with a mass tens of thousands of times greater than our Sun from its very first moment. It is within the violent throes of this birth that a gamma-ray burst could potentially be unleashed. The properties of such a burst would be fundamentally different from those produced by a collapsing star. For one, the timescale would be unique. Without a stellar envelope for a jet to drill through, the burst might be incredibly brief, perhaps lasting only milliseconds, or it could be unusually long, powered by the continuous feeding of the collapsing cloud over a longer period. The spectrum of the gamma rays might also carry a distinct fingerprint, reflecting the different composition and density of the infalling primordial gas compared to the interior of a mature star. Most importantly, there would be no accompanying supernova. The event would be a pure black hole birth, a flash of light signaling the abrupt appearance of a gravitational giant in the early universe with no stellar explosion to mark its passing. The motivation for searching for these phantom bursts is deeply connected to one of the great puzzles in modern cosmology, the origin of supermassive black holes. We now know that galaxies in the very young universe observed by the James Webb Space Telescope already host black holes at their centers weighing billions of suns. It is incredibly difficult to explain how a stellar mass black hole, formed from the collapse of a single star, could have grown to such an immense size in just a few 100 million years. A direct collapse black hole provides a perfect solution. It offers a ready-made seed, already tens of thousands of solar masses at birth, giving it a colossal head start on its growth spurt through accretion. Detecting a gamma-ray burst from such an event would be the smoking gun, direct evidence for this rapid formation pathway. The hunt for these events is the ultimate challenge, pushing our observational capabilities to their absolute limit. They would be exceedingly rare, as the conditions for direct collapse are thought to be very specific. Their extreme redshift would place their emission deep into the infrared, likely beyond the reach of current gamma-ray satellites. Future missions designed with larger detectors and greater sensitivity to higher energy photons might be the key. The discovery of such a burst would not just break a distance record. It would open a window into a previously invisible chapter of cosmic history, revealing a mechanism for creating cosmic structure that operated before the first stars ever began to shine. It would show us that the universe's first light came not only from the furnaces of stars, but also from the gravitational fires of black holes being born directly from the darkness. To truly grasp the violent ballet of a gamma-ray burst, we must venture beyond what telescopes can see and into the realm of pure mathematics and computational power. The actual event, from the core collapse of a massive star to the emergence of a relativistic jet, happens in a realm of such extreme gravity, temperature, and density that it is fundamentally unobservable. This is where the power of numerical simulations becomes absolutely essential. Using some of the world's most powerful supercomputers, astrophysicists can create virtual laboratories to recreate these cosmic cataclysms, testing our theories against the unforgiving laws of physics in a way that mere observation never could. These simulations are not just simple animations. They are intricate digital universes governed by millions of lines of code that solve the complex equations of magnetohydrodynamics and general relativity, allowing us to witness the unseeable. The journey of a simulation often begins at the moment of stellar death. The model starts with a virtual star defined by its mass, rotation rate, and chemical composition. Then the trigger is pulled. The star's core is forced to collapse under its own immense weight. What happens next is a cascade of physical processes that the simulation must track with exquisite detail. The infalling material forms a hot, dense accretion disk around the newborn black hole, a maelstrom of matter spinning at near-light speeds. It is here, in the intense gravitational and magnetic fields just outside the event horizon, that the jet is born. The simulations show how the star's own magnetic field, amplified by the rapid rotation of the core, can be wound up into a tightly coiled spring of energy. This magnetic spring then drives a channel of ultra-hot plasma upward, punching its way through the surrounding stellar material. Watching this process unfold in a simulation, you see the jet struggle against the weight of the star, sometimes flickering or stalling before it finally breaks free, a testament to the titanic forces at play. But launching the jet is only half the battle. The simulation must then follow this pencil-thin beam of energy as it travels through the remainder of the star. This is a critical phase that determines the burst's duration and structure. The jet must drill through the stellar envelope, and its interaction with this material shapes its final properties. Simulations reveal that the jet is not a smooth, solid beam, but is instead unstable, prone to wobbling and developing internal turbulence. As it pushes outward, it gathers a cocoon of hot, shocked stellar material around it. This cocoon plays a crucial role, collimating the jet, keeping it focused and influencing the mix of particles and radiation that will eventually be unleashed into interstellar space. The entire sequence, from core collapse to jet breakout, might take only tens of seconds in real time, but simulating it can require months of continuous calculation on a supercomputer, crunching numbers for every tiny parcel of gas in the virtual star. The ultimate value of these digital experiments lies in their ability to make testable predictions. Once a simulation has produced a virtual gamma-ray burst, it generates a synthetic light curve and spectrum, a prediction of what telescopes like Swift and Fermi should see if the model is correct. Scientists then compare this digital prediction to the actual data from a real gamma-ray burst. Does the simulated burst last as long as the observed one? Does its light curve show the same patterns of brightening and fading? Does the distribution of gamma-ray energies match? It is this rigorous comparison that allows us to refine our models. For instance, early simulations that did not include sufficiently strong magnetic fields produced jets that were too weak and slow. It was only by incorporating the crucial role of magnetohydrodynamics that simulators could create jets with the relativistic speeds needed to match observations. This iterative process of simulation and observation is what sharpens our understanding of the most distant bursts. When we detect a gamma-ray burst from 13 billion light-years away, its light carries an encoded story of its progenitor star and the explosion mechanics. Numerical models provide the dictionary to translate that story. They help us answer questions like, how massive was the star that died? How fast was it spinning? What was the density of the gas surrounding it? By running thousands of simulations with slightly different initial conditions, a heavier star, a slower rotation, a stronger magnetic field, researchers can essentially work backwards, finding the digital model that best reproduces the unique signature of the observed burst. In this way, supercomputer simulations act as a bridge, connecting the fleeting flash of light captured by our satellites to the profound physical reality of a star's death and the birth of a black hole at the edge of time. But what about all those gamma-ray bursts happening across the cosmos whose jets are pointed away from us? Are they simply lost to the darkness, their stories forever untold? This question leads us to one of the most intriguing hunting grounds in modern astronomy, the search for the orphan afterglow. Imagine a lighthouse on a distant, stormy coast. If its powerful beam is sweeping across the ocean, you only see a brilliant flash if you happen to be looking directly down the path of the light. But what about the areas the beam never touches? They remain in shadow. In the case of a gamma-ray burst, we are only blinded by the light if we are in the narrow path of the jet. The vast majority of these explosions are happening with their beams aimed in other directions, completely invisible to our gamma-ray satellites. However, the story doesn't necessarily end there. While the initial ultra-relativistic jet is tightly focused, the material that follows creates a different kind of phenomenon. As the jet slams into the surrounding interstellar gas, it creates a shock wave that expands outward. This shock wave is not nearly as focused as the original jet. Over time, as it plows into more and more material, it begins to slow down and decelerate. When it drops below relativistic speeds, its emission becomes much more isotropic, meaning it begins to radiate more evenly in all directions. This is the orphan afterglow. It's the lingering, faint glow, primarily in radio waves, that would be visible even to observers who are not in the direct line of fire of the initial gamma-ray beam. It would appear as a mysterious, slowly brightening and then fading radio source with no cataclysmic gamma-ray flash to explain its origin. Finding such an orphan would be a monumental discovery. It would confirm a key prediction of the relativistic jet model, and more importantly, it would open up an entirely new way to take a census of stellar cataclysms. We would no longer be limited to the small fraction of bursts whose jets are pointed at us. We could start to count the ones we've been missing. This would allow us to calculate the true rate of gamma-ray bursts in the universe, moving from a biased sample to a complete picture. Are these events 10 times more common than we think? 100 times? The answer would tell us just how frequently massive stars die in this most violent fashion, providing a crucial data point for models of stellar evolution and cosmic chemical enrichment. The hunt for these cosmic orphans is incredibly challenging, a true test of patience and advanced technology. The radio afterglow from an off-axis burst would be extremely faint and rise to its peak brightness very slowly, over weeks or even months, as the shock wave gradually decelerates and its emission becomes more visible to us. Detecting it requires large radio telescopes like the Very Large Array in New Mexico that can conduct deep, sensitive surveys of the sky and then compare them over long periods to spot new, transient sources that weren't there before. Astronomers would then have to rule out all other possible explanations for a fading radio source, such as a distant supernova or activity from an active galactic nucleus, before they could confidently claim to have found a true orphan. While several candidates have been studied over the years, a definitive, uncontested detection remains elusive, making the orphan afterglow one of the holy grails of time domain astronomy. Its discovery would not just be about finding a single lost explosion. It would be like turning on a light in a dark room, revealing a population of cosmic cataclysms that have been hiding in plain sight all along. The environment in which a star is born fundamentally shapes its entire life, and perhaps most dramatically, its death. We've seen how the most distant gamma-ray bursts act as probes into the early universe, but this raises a deeper question. Why are these colossal explosions so much more common in the infant cosmos than they are today? The answer lies in a crucial and surprisingly specific ingredient that seems to be essential for creating a gamma-ray burst progenitor: a distinct lack of heavy elements. Astronomers refer to this as the metallicity threshold, a concept that explains not only the prevalence of bursts in the past but also guides us on where to find them in our own cosmic neighborhood. First, let's clarify what astronomers mean by metals. In a definition that would baffle a chemist, any element heavier than helium is considered a metal in the cosmic lexicon. Hydrogen and helium were forged in the Big Bang, but every other element, the carbon in our bodies, the oxygen we breathe, the iron in our blood, was created later in the nuclear furnaces of stars and scattered across space by their explosive deaths. Therefore, the metallicity of a gas cloud or a galaxy is a direct measure of its history of stellar activity. A low metallicity environment is a primitive one, relatively unpolluted by the ashes of previous stellar generations. And it is in these pristine conditions that the recipe for a long gamma-ray burst finds its most potent form. The connection hinges on the life cycle of a massive star. For a star to die in a gamma-ray burst, it needs to retain two key properties right up to the moment of its core collapse: a very large mass and an extremely rapid rate of rotation. The rapid spin is crucial for winding up magnetic fields and launching the narrowly focused jets. This is where metallicity becomes the deciding factor. In a metal-rich environment like our modern Milky Way, massive stars are born with a significant amount of heavy elements in their outer layers. These elements make the star's atmosphere more opaque, allowing the intense radiation from its core to push on the gas more effectively. This results in powerful stellar winds that constantly blow material off the star's surface over its lifetime. This mass loss has a double whammy effect. First, it steadily reduces the star's mass, potentially bringing it below the threshold needed for a dramatic collapse. Second, and even more critically, as the star loses mass, it also loses angular momentum. Its spin slows down. It's the astrophysical equivalent of a spinning ice skater extending their arms to slow their rotation. By the time a metal-rich massive star is ready to die, its core may be rotating too slowly to power the relativistic jets required for a gamma-ray burst, leading instead to a more common and less focused type of supernova. Now contrast this with a star born in a low metallicity environment, like a dwarf galaxy or the early universe. The gas it forms from is pure, composed almost entirely of hydrogen and helium. Without heavy elements to increase the opacity, the star's stellar winds are much weaker. It holds onto its mass tenaciously throughout its life. More importantly, it retains its rapid rotation. The star spins furiously from birth to death, its core remaining a tightly wound spring of rotational energy. When this star finally exhausts its nuclear fuel and its core collapses, all that stored rotational energy is available to be channeled by magnetic fields into the ultra-fast, narrowly collimated jets that create a gamma-ray burst. The low metallicity acts as a preservative, allowing the star to maintain the precise conditions needed for a catastrophic, jet-producing death. This metallicity threshold provides a powerful explanation for the observed cosmic distribution of gamma-ray bursts. It's why we see so many of them at high redshifts. The early universe was, by definition, a low metallicity environment. The first stars, population 3 stars, formed from perfectly pristine gas, making them ideal candidates for producing the most extreme bursts. As the universe aged and became chemically enriched by successive generations of stars, the overall metallicity rose and the rate of gamma-ray bursts correspondingly declined. This is also why, in our local universe, we don't see long GRBs in grand spiral galaxies like Andromeda or our own Milky Way. These galaxies are metal-rich and have been for billions of years, making them infertile ground for gamma-ray burst progenitors. Instead, when a long GRB does occur nearby, it is almost always found in a small, irregular, or dwarf galaxy, a galactic environment that has undergone less chemical evolution and still retains some of the primitive conditions of the cosmic dawn. This understanding has turned the metallicity threshold into a practical tool for astronomers. It tells us exactly where to point our telescopes when hunting for these events. Surveys focused on identifying metal-poor, actively star-forming dwarf galaxies are essentially creating a map of the most likely GRB nurseries in the local universe. This bias also helps solve puzzles such as the no-host galaxy problem for some bursts. If a GRB progenitor was a runaway star ejected from a low metallicity dwarf galaxy, its explosion would occur far from its visible birthplace, appearing as an orphan in the darkness between galaxies. The metallicity connection is more than just a curious astrophysical detail. It is a fundamental part of the narrative of cosmic evolution, linking the violent deaths of individual stars to the large-scale chemical enrichment of the cosmos, and explaining why the universe's most brilliant flashes are ultimately a testament to its most primitive conditions. The link between short gamma-ray bursts and the ripples in spacetime known as gravitational waves represents one of the most thrilling convergences in modern astrophysics. a connection that moved from theoretical prediction to spectacular reality in 2017. That year, on August 17th, the LIGO and Virgo gravitational wave observatories detected a signal unlike any they had seen before. Coded GW170817, the signal was the distinctive chirp of two neutron stars spiraling together, a crescendo that lasted for about 100 seconds before culminating in a final merger. Just 1.7 seconds after this gravitational wave signal peaked, NASA's Fermi Gamma Ray Space Telescope and independently the Integral satellite recorded a short gamma ray burst from the exact same region of the sky. This was not a coincidence, it was the confirmation of a decades-old hypothesis. For the first time, we had witnessed the same cosmic cataclysm through two completely different messengers, the rippling of spacetime itself and a flash of light. This event, GW170817, was a transformative moment for multi-messenger astronomy. The gravitational wave signal provided a direct measure of the masses of the merging neutron stars and the distance to the event, which was a relatively close 130 million light-years away in the galaxy NGC 4993. The detection of the short gamma-ray burst confirmed that such mergers do indeed produce relativistic jets, but the observations didn't stop there. The precise localization allowed every major telescope on Earth and in space to swing into action, capturing the event across the electromagnetic spectrum. They witnessed the resulting kilonova, the radioactive glow from the neutron-rich debris that revealed the forge where heavy elements like gold and platinum are created. This single event tied together gravity, high-energy physics, and cosmic chemistry in a single, elegant package, proving that short gamma-ray bursts are the brilliant electromagnetic signatures of neutron star collisions. While GW170817 was a watershed moment, its relative proximity also highlights a current limitation. The gravitational wave signals from such mergers are incredibly faint, and our current detectors like LIGO and Virgo can only sense them from a cosmological stone's throw away within a few 100 million light-years. This means that the vast majority of short gamma-ray bursts, which can be detected from billions of light-years away, are currently beyond the reach of our gravitational wave ears. We see their brilliant light, but we cannot yet hear the spacetime ripple that accompanies them. This leaves a wealth of information locked away, as the gravitational wave signal carries unique details about the pre-merger dynamics, the final moments of the inspiral, and the properties of the ultra-dense matter that makes up neutron stars. The future, however, promises to shatter this distance barrier. Next-generation gravitational wave observatories are on the drawing board. Projects like the Laser Interferometer Space Antenna, or LISA, which would consist of 3 spacecraft flying in a giant triangular formation millions of kilometers apart. A space-based observatory like LISA would be immune to the seismic noise that limits ground-based detectors, allowing it to sense gravitational waves at lower frequencies. This would make it exquisitely sensitive to the early inspiral phase of massive black hole binaries, but it could also detect neutron star mergers much earlier in their dance and from vastly greater distances. Another proposed project, the Einstein telescope, is envisioned as a ground-based detector with vastly improved sensitivity, using cryogenic technology and a triangular configuration to listen for these cosmic ripples from the edge of the observable universe. The scientific payoff of detecting a gravitational wave signal from a distant short gamma-ray burst would be immense. By comparing the arrival time of the gravitational wave, which travels unimpeded through the cosmos, with the light from the burst, we could perform an extremely precise test of a fundamental tenet of Einstein's theory, that gravity travels at the speed of light. Any deviation, however tiny, would have revolutionary implications for physics. Furthermore, the gravitational wave signal would act as a direct probe of the neutron stars themselves, revealing their tidal deformability, a measure of how squishy they are, which in turn tells us about the nature of matter under densities far greater than anything we can create in particle accelerators. This would resolve long-standing debates about the equation of state of neutron star matter. Catching a short GRB and its gravitational wave signal from the cosmic dawn would be the ultimate prize, offering a glimpse into whether neutron star mergers happened with different properties in the early, denser universe, and potentially revealing a new pathway for the rapid creation of heavy elements that paved the way for the first planets and the potential for life. Looking ahead, the next generation of gamma-ray burst hunters is already taking shape, poised to dramatically expand our view of the high-energy universe. The journey that began with pioneering missions like SWIFT and Fermi is set to continue with even more advanced observatories, specifically engineered to push further back in time and capture the faintest whispers from the cosmic dawn. Leading this charge are two key missions, the imminent SVOM, or Space Variable Objects Monitor, and the ambitious concept study for Theseus, the transient high-energy sky and early universe surveyor. These instruments represent an evolutionary leap designed not just to find more bursts but to find the ones that have, until now, remained beyond our grasp. The Sino-French SVOM mission is a direct successor to SWIFT, honed by 2 decades of lessons learned. Its strategy is one of refined efficiency and enhanced sensitivity. Like SWIFT, SVOM will carry a suite of instruments working in harmony, a gamma-ray monitor to detect the initial explosion, and an X-ray telescope to rapidly pinpoint the location. But SVOM's crucial advantage lies in its addition of a visible light telescope mounted directly on the spacecraft. This means it can begin observing the optical afterglow within minutes, without waiting for a signal to be relayed to ground-based telescopes, shaving off precious time in the race against the fade. Furthermore, its instruments are tuned to be particularly sensitive to high redshift bursts. They are optimized to detect the relatively softer, longer-duration gamma-ray emission that is a hallmark of bursts whose light has been stretched into the lower-energy X-ray band by extreme cosmological redshift. SVOM will act as a precision scalpel, expertly finding and characterizing the bursts that signal the deaths of the earliest stars. While SVOM represents the next logical step, the proposed Theseus mission is a paradigm shift, a spacecraft designed from the ground up to conduct a complete census of the transient high-energy sky with a primary goal of exploring the early universe. Its most powerful tool would be an infrared telescope, a first for a GRB-dedicated mission. This is a game-changing capability. For the most distant bursts whose optical light is redshifted deep into the infrared, Theseus wouldn't have to wait for alerts from ground-based observatories that struggle with atmospheric interference. It would itself be the premier instrument for follow-up, capable of measuring redshifts out to values of 10 or more directly from orbit. Imagine a scenario where Theseus detects a gamma-ray flash, and within minutes, its own infrared telescope is gathering the spectrum of the afterglow, immediately revealing that this star died when the universe was only 400 million years old. This all-in-one approach would revolutionize the field. The scientific promise of these missions is a flood of new, statistically significant data. Currently, we have a handful of confirmed gamma-ray bursts from redshifts beyond 6. Theseus, in particular, could detect dozens, perhaps even hundreds of such events each year. This vast sample would transform our understanding from studying individual, exotic cases to analyzing a true population. We could move from asking what happened in this one galaxy to answering fundamental questions about the early universe as a whole. What was the typical mass of the first stars? How quickly did the first galaxies become chemically enriched? Did the properties of gamma-ray bursts evolve over the first billion years? With a large enough sample, the patterns hidden within the light curves, energies, and host galaxy environments of these ancient bursts will paint a detailed picture of cosmic evolution during its most formative era. These future missions also promise to solve long-standing mysteries. They will have the sensitivity to definitively study the dark gamma-ray burst population, those events hidden by dust, by catching their afterglows in the infrared where dust is transparent. They could finally detect a short-duration burst from the cosmic dawn, which would have profound implications for our understanding of how quickly binary neutron star systems could form and merge. Furthermore, their rapid alert systems and precise localizations will be a boon for multi-messenger astronomy, providing the best possible targets for the next generation of gravitational wave detectors and neutrino telescopes, creating a web of observatories all working in concert to dissect these cosmic cataclysms. The future of gamma-ray burst astronomy is not just about seeing further, it's about seeing more clearly, more completely, and in greater coordination than ever before, turning the violent deaths of the first stars into our most powerful lens on the origin of everything. Contemplating a flash of light that has journeyed for over 13 billion years inevitably forces a perspective shift that is as humbling as it is enlightening. These distant gamma-ray bursts are more than just astrophysical phenomena. They are profound philosophical statements written across the cosmos. They tell a story that predates not just humanity, but our planet, our sun, and even the Milky Way galaxy itself. Each detection is a direct encounter with a time when the universe was a fundamentally different place, a violent, chaotic, and intensely creative forge where the very rules of existence were being written in fire. To study them is to understand that the calm, structured cosmos we see today is the product of an ancient age of titanic upheaval, an era whose echoes we are only now beginning to decode. This perspective challenges the intuitive, Earth-centered view we so easily adopt. From our planetary vantage point, the universe can seem static and eternal, with stars fixed in their constellations. But gamma-ray bursts shatter this illusion of permanence. They reveal a cosmos in a state of relentless flux, where stars are not gentle twinkling lights but colossal engines of creation and destruction. The fact that we can witness the death of a star from the universe's infancy demonstrates that we are not separate observers looking in on a finished product. We are embedded within this ongoing narrative, living on a world made possible by the very processes we are observing. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all forged in the hearts of massive stars that lived and died long before our solar system coalesced from their ashes. We are quite literally stardust that has become conscious, looking back to trace its own origin story. This realization carries a dual message of fragility and significance. On one hand, the sheer power of these events is a stark reminder of our physical vulnerability. A gamma-ray burst occurring within a few thousand light-years of Earth would pose an existential threat, its radiation capable of stripping away our protective ozone layer and triggering a mass extinction. Our peaceful corner of the galaxy is a temporary haven in a universe that can be unimaginably hostile. Yet, on the other hand, our ability to detect, analyze, and comprehend these events from the edge of time is a testament to the extraordinary power of the human intellect. The same cosmic processes that could so easily erase us have also given rise to a species capable of unraveling their secrets. We are the universe become self-aware, using the laws of physics to understand its own violent and magnificent history. Ultimately, the study of the most distant gamma-ray bursts is a journey into our own cosmic ancestry. They are the brilliant, fleeting gravestones of the first generations of stars, the pioneers that lit up the darkness and seeded the cosmos with the heavy elements necessary for planets and life. By analyzing their light, we are reading the diary of the universe's youth, learning about the conditions that made our existence possible. This knowledge doesn't diminish our place in the cosmos, it redefines it. We are not accidental inhabitants of a random rock, but the temporary custodians of a rich legacy, the product of 13.8 billion years of cosmic evolution. Each new burst detected is a chapter added to this grand story, a story that connects the fiery death of a star at the dawn of time to the curious minds on a pale blue dot, gazing up at the night sky and daring to ask where it all began. Now, while the most distant gamma-ray bursts offer a glimpse into the universe's infancy, some of the most transformative insights have come from events remarkably close to home, where the unprecedented level of detail allows us to dissect the physics of these explosions with surgical precision. This brings us to a truly extraordinary event, a gamma-ray burst that broke all the conventional rules and revealed a phenomenon that might be a hidden signature of many stellar deaths, GRB 060218. Detected by NASA's Swift satellite on February 18, 2006, this burst immediately stood out not for its raw power but for its astonishing longevity and proximity. While most bursts are brilliant, fleeting flashes from across the cosmos, this one was a slow, luminous burn happening in our own cosmic backyard, a mere 440 million light-years away in the constellation Aries. What made GRB 060218 so unusual was its duration. Instead of lasting for the typical minute or less, it emitted gamma rays and X-rays for over half an hour, an eternity in the world of gamma-ray bursts, classifying it as an ultra-long event. This extended emission pointed to a unique type of stellar demise. The leading theory suggests that the progenitor was not a typical Wolf-Rayet star, but a much larger blue supergiant. A blue supergiant retains its massive hydrogen envelope, creating a star with a radius hundreds of times larger than that of a typical GRB progenitor. When the core of such a star collapses, the relativistic jet has a much longer and more arduous journey to escape the stellar interior. It must drill through this immense shroud of gas for thousands of seconds, explaining the prolonged duration of the gamma-ray emission as the jet struggles to break free. We were essentially witnessing a stellar death in extreme slow motion. But the most fascinating revelation from this event came not from the initial blast but from what followed. As astronomers tracked the afterglow across different wavelengths, they noticed something peculiar in the ultraviolet and optical light. The brightness of the afterglow did not fade in a perfectly smooth, predictable manner. Instead, it showed a distinct rebrightening, a secondary peak that emerged days after the initial explosion. This was the signature of a dust echo. Here's how it works. The initial flash of the gamma-ray burst and the ensuing ultraviolet light from the supernova act like a cosmic camera flash, illuminating everything around it. This intense pulse of radiation travels outward at the speed of light. If it encounters a shell or cloud of dust located some distance from the explosion, perhaps material ejected by the star in an earlier, calmer phase of its life, the light will scatter off the tiny dust grains. This scattering process creates an echo. The light is not absorbed, it is redirected. Some of that scattered light is sent on a new path toward Earth, but because it had to travel to the dust cloud and then back toward us, it arrives later than the light that came to us directly. This delay creates the observed rebrightening, a delayed pulse of light that carries with it specific information about the dust itself. By analyzing the timing and the color of this echo, astronomers can determine the distance of the dust cloud from the explosion site and even infer the composition and size of the dust grains. In the case of GRB 060218, the dust echo provided a direct probe of the immediate environment around the star in the years leading up its catastrophic collapse, revealing a history of mass loss and the structure of its circumstellar material. The significance of this discovery extends far beyond this single, nearby event. Dust echoes are not unique to GRB 060218. They are likely a common feature of many stellar explosions, including supernova. For distant gamma-ray bursts, however, detecting such a subtle echo is incredibly challenging. The signal is faint and requires sustained, multi-wavelength observations over weeks. Yet the potential payoff is enormous. If we can detect dust echoes in the afterglows of bursts from the cosmic dawn, they would serve as powerful tools for studying the interstellar environments of the very first galaxies. Finding dust that early in the universe's history would be a startling discovery, indicating that the first generations of stars had already produced and scattered heavy elements with astonishing speed, rapidly transforming their primitive surroundings. GRB 060218, therefore, serves as a nearby laboratory, a Rosetta Stone that helps us interpret the more subtle signals we might one day detect from the edge of time, where every flicker of light holds a clue to the construction of the early cosmos. Measuring the exact distance to these cosmic beacons is one of the most delicate and challenging tasks in all of astronomy. The entire endeavor hinges on obtaining a precise redshift value, the Z number that tells us how much the universe has stretched during the light's journey. For gamma-ray bursts, this isn't a simple matter of snapping a picture. It requires capturing and dissecting the faint, fleeting light of the afterglow with a level of precision that pushes our technological capabilities to their absolute limit. The primary method, and the gold standard for accuracy, involves analyzing the afterglow's spectrum for a specific set of fingerprints known as absorption lines. This technique works because the brilliant afterglow doesn't just travel through empty space. On its multi-billion-year journey to Earth, its light passes through various clouds of gas both within its host galaxy and in the vast intergalactic medium. The atoms in these clouds act like selective filters, absorbing very specific wavelengths of light that correspond to the energy needed to excite their electrons. Each element has its own unique pattern of these absorption lines. When astronomers spread the afterglow's light into a detailed spectrum, they look for these patterns. However, because the universe is expanding, the entire pattern is shifted toward the red end of the spectrum. By identifying a familiar pattern, like the signature of magnesium or silicon, and measuring exactly how far it has been redshifted from its known rest wavelength, scientists can calculate the redshift with extraordinary precision. This method is so powerful because it uses the burst itself as a backlight, illuminating the material in front of it and providing a direct, clean measurement of the cosmic expansion that has occurred. But there's a catch, and it's a significant one. To see these absorption lines clearly, you need a high-resolution spectrum with an excellent signal-to-noise ratio. In simple terms, the signal is the actual light from the afterglow. The noise is the random background light from the sky, the atmosphere, and the telescope's own electronics. For a distant gamma-ray burst, the afterglow is incredibly faint, and it's fading fast, collecting enough photons to build a spectrum with sharp, well-defined absorption lines is a race against time. It requires the rapid response of the world's largest telescopes, like the Keck Observatory or the Very Large Telescope, and even then, they often need to take exposures lasting tens of minutes to an hour. During this time, the afterglow is becoming dimmer, which means the later photons contribute less to the signal, making the task even harder. If the spectrum is too noisy, the absorption lines become blurred and uncertain, like trying to read a fingerprint smudged with dirt, leading to a redshift measurement that might have a large margin of error. When the afterglow has faded beyond detection, astronomers turn to a secondary, though less precise, method, measuring the redshift of the host galaxy itself. This involves taking a long-exposure image of the empty spot where the burst occurred, patiently gathering the faint, integrated light of the entire galaxy over many hours. The spectrum of this galaxy will show emission lines, bright spikes of light at specific wavelengths caused by hot, glowing gas, often from regions of active star formation. These emission lines also get redshifted, and they can provide a redshift measurement for the galaxy and, by association, for the burst that happened within it. However, this method comes with its own set of uncertainties. The gamma-ray burst might not have occurred exactly at the center of the galaxy. It could have been in a distant spiral arm or even in a satellite galaxy that is too faint to see. The measured redshift of the host galaxy's bright core might not perfectly match the exact location of the burst, introducing a small but potentially important error. For the most distant bursts, the host galaxies are so faint that obtaining any spectrum at all is a monumental achievement, and the emission lines might be too weak to provide a confident redshift. This constant battle against faintness and noise means that every redshift measurement for a high-distance gamma-ray burst carries with it a stated uncertainty. A burst might be reported as having a redshift of z equals 9.4 plus or minus 0.3. That plus/minus factor represents the range within which the true value likely lies. For cosmological studies, this uncertainty is crucial. When we use these bursts to map the expansion rate of the universe or to study the conditions of the early cosmos, that margin of error must be carefully factored into the conclusions. The hunt for the most distant burst ever is not just about finding one with a high redshift. It's about finding one whose redshift can be measured with high confidence, turning a tantalizing possibility into a firm data point that can reliably advance our understanding of the cosmic dawn. But just before the main cataclysm unleashes its full fury, some of these stellar giants send out a cryptic warning. A select group of gamma-ray bursts exhibit a bizarre and fleeting phenomenon, a weak, short-lived flash of gamma rays that flickers into existence seconds or even minutes before the colossal main event. These are known as precursor flares, and for astronomers, they are like a faint, distant drumbeat signaling the final moments of a star's collapse. Detecting these precursors, especially in bursts from the cosmic dawn, is like finding a fossilized footprint right beside the skeleton. It provides a crucial clue about the final steps that led to the cataclysm. The leading explanation for these precursor flares takes us back inside the doomed star during its last chaotic seconds. As the core collapses and the relativistic jet begins to form, it doesn't instantly blast its way out into space. It first has to travel through the star's immense interior, a journey that is anything but smooth. This jet is a titanic drill pushing against the overwhelming weight of the stellar material. The precursor flare is thought to be the moment this jet, or the initial shock wave associated with it, first punches through the star's surface. Imagine a submarine finally breaking through a thick layer of polar ice. The first sign is a small crack and a spray of water, followed moments later by the full vessel erupting into view. In the same way, the precursor is that initial crack, a small release of energy as the jet breaches the stellar surface. The main gamma-ray burst then follows when the full, unimpeded jet escapes, screaming into the interstellar void. For observers, these precursors are more than just a cosmic curiosity. They are a potential diagnostic tool. The properties of the precursor, its brightness, duration, and the energy of its gamma rays could reveal vital information about the structure of the progenitor star. A stronger, harder precursor might suggest the star had a particularly thick and dense outer envelope, requiring a more violent initial breakout. A weaker precursor could point to a star that had already shed most of its outer layers, offering less resistance to the jet. By studying precursors across a range of bursts, astronomers can effectively perform an autopsy on the star, understanding its size, composition, and density profile just before it died. The hunt for these signals in the most distant gamma-ray bursts adds another layer of profound significance. A precursor detected from a burst at a redshift of 9 would be a direct probe of the anatomy of one of the universe's very first stars. Did these population 3 behemoths have extended, puffy envelopes, or were they more compact? The characteristics of the precursor could provide the answer. However, detecting such a faint, brief signal from the edge of the observable universe is a monumental challenge. The precursor's light is stretched and dimmed by its immense journey, often blending into the background noise or arriving so close to the main event that satellites struggle to distinguish it. It requires incredibly sensitive instruments and sophisticated software to tease these subtle first whispers from the data. Successfully identifying a precursor in an ancient burst would complete a timeline of stellar death with unprecedented detail. We would have a timestamp for the jet's breakout, followed by the main energy release. This sequence allows scientists to test and refine the most complex computer simulations of these events. If the simulated jet in a model takes too long or too little time to break out compared to the observed precursor delay, it tells the modelers they need to adjust their assumptions about the star's internal structure or the jet's power. In this way, these faint, preemptive flashes serve as a crucial reality check for our theories, ensuring that our understanding of the most violent explosions in the cosmos is built not just on the brilliant main event, but on the entire, intricate story of the star's final moments. This spirit of discovery extends far beyond the walls of professional laboratories and university departments, thanks to a fundamental principle in modern astronomy: open data. The incredible observations collected by satellites like Swift and Fermi don't just vanish into a private database. Instead, they are meticulously processed and then released to the entire world through public archives, most notably NASA's High-Energy Astrophysics Science Archive Research Center, known as HERSRC. This isn't a simple data dump. It's a carefully curated library of cosmic events, where every detected gamma-ray burst has its own digital dossier containing the precise timing of the gamma-ray photons, the light curves across different energy bands, the coordinates pinpointed by the X-ray telescope, and often the follow-up observations from other telescopes. This commitment to open access transforms these multi-million-dollar missions from exclusive instruments into global resources, empowering a worldwide community of scientists and students. The impact of this openness is profound. A graduate student in India, an amateur astronomer in Germany, or a high school teacher in Chile can, with an internet connection, download the exact same dataset that the mission scientists are using. They can apply their own analytical techniques, test new theoretical models, or simply explore the raw data from a cataclysm that occurred billions of years ago. This democratization of data accelerates the pace of science dramatically. Instead of a single team working on a problem, you have hundreds of independent minds around the globe, each bringing their unique perspective and expertise to the table. Some of the most interesting discoveries about gamma-ray bursts have come from researchers who were not part of the original detection teams, people who noticed a subtle anomaly in a light curve or found a novel way to classify bursts that others had missed. This collaborative, crowd-sourced approach to knowledge is a powerful engine for innovation. For students, these archives are an invaluable gateway into real scientific research. University courses on high-energy astrophysics often use HERSRC as a primary textbook. A common assignment is to download the data from a specific burst, like the record-breaking GRB 090423, and learn how to measure its duration, analyze its spectrum, and calculate its redshift. This hands-on experience moves learning from abstract equations to tangible discovery, allowing the next generation of astronomers to develop the skills they'll need to run the observatories of the future. It fosters a sense of direct engagement with the cosmos, proving that you don't need a doctorate to begin asking meaningful questions about the universe's most extreme events. The archive ensures that the legacy of a mission like Swift continues long after its instruments fall silent, serving as an eternal resource for education and inspiration. This model of open science also builds a crucial layer of transparency and reproducibility into the scientific process. When a research team publishes a paper claiming a new discovery about gamma-ray bursts, their fellow scientists can immediately access the underlying data to verify the results or attempt to replicate the analysis. This is the bedrock of the scientific method. It prevents errors from propagating and ensures that our understanding of the cosmos is built on a foundation of evidence that is available for all to scrutinize. The public archive stands as a testament to the idea that the quest to understand the universe is a human endeavor, one that benefits immensely from shared curiosity, collaborative spirit, and the free flow of information, ensuring that every brilliant flash from the edge of time becomes a gift to the collective knowledge of our species. And so we arrive at our final fact, a powerful reminder that for all we have learned, the cosmos still holds profound mysteries. The story of gamma-ray burst 070125 is not one of a record-breaking distance or a revolutionary discovery, but of a stubborn, lingering question mark. Detected in January 2007, this was an exceptionally energetic long-duration burst, precisely the kind of event we would expect to be the death cry of a massive star. Swift pinpointed its location, and astronomers around the world swung their telescopes toward the spot, fully anticipating the familiar sequence, a fading afterglow leading them to a faint, distant galaxy. The afterglow appeared right on cue, allowing for a redshift measurement that placed the burst a respectable several billion light-years away. But when the afterglow faded and the world's most powerful eyes, including the Hubble Space Telescope, stared deeply at that empty patch of sky, they saw nothing. No smudge of light, no hint of a stellar nursery, no host galaxy whatsoever. This was not a case of a galaxy simply being too faint to see. This was a profound absence. The region was a virtual void, a blank canvas in the cosmic web. This makes GRB 070125 a monumental paradox. According to our well-tested collapsar model, long gamma-ray bursts are inextricably linked to the deaths of massive, short-lived stars. Such stars simply do not have the time to wander far from their birthplace. They are tethered to the dense, gas-rich regions of galaxies where they formed. For a burst this powerful to occur in the middle of intergalactic space is like finding the wreckage of a massive ocean liner on the peak of a mountain range, far from any sea. It defies the fundamental logic of stellar life cycles. The most compelling explanation is also the most dramatic, that this star was a true cosmic exile, a runaway of epic proportions. We know that gravitational interactions in dense star clusters can fling stars outward at tremendous speeds. It is conceivable that the progenitor of GRB 070125 was violently ejected from its home galaxy millions of years before its death, destined to explode in the profound emptiness between galaxies. The environment around the burst supports this idea. Analysis of its afterglow suggested it was expanding into an unusually low-density medium, exactly what you would expect in the lonely intergalactic void. This solitary death highlights the dynamic and sometimes chaotic nature of galactic ecosystems, where stars are not always sedentary citizens but can be cast out into the darkness. Yet, even this elegant solution raises new questions. Could a massive star survive long enough to travel the immense distance required to reach such an empty region? The journey would take millions of years, a significant fraction of the star's total lifespan. Alternatively, could the burst have occurred in a faint, diffuse galaxy that is simply too dark for even Hubble to detect, a ghost of a galaxy made mostly of dark matter? Or does this enigmatic event point to a rarer, more exotic pathway for creating long gamma-ray bursts, one that doesn't require a massive star born in a typical galactic environment? GRB 070125 stands as a permanent counterexample, a challenge to our neatly defined categories, ensuring that our catalogue of 50 facts remains an open-ended document, a chapter in a story that is still being written. It is a humbling and thrilling note to end on, a symbol of the endless curiosity that drives us to keep looking up, knowing that the next flash of light could bring either a satisfying answer or a deeper, more beautiful mystery. And so, our journey to the edge of the observable universe brings us to a profound realization. These distant gamma-ray bursts are far more than just the universe's most spectacular fireworks. They are fundamental scientific instruments, each one a precisely calibrated probe sent to us from the cosmic dawn. They are nature's own time machines, allowing us to witness the violent deaths of the first stars and the chaotic environments of the earliest galaxies in a way that would otherwise be utterly impossible. Every flash of gamma rays is a message carefully encoded with information about the conditions of the infant cosmos, carrying secrets about the formation of black holes, the synthesis of heavy elements, and the clearing of the primordial fog. This entire field of study is currently undergoing a revolution driven by the unparalleled power of the James Webb Space Telescope. Where we once struggled to see even the faintest glimmer of a host galaxy, Webb now reveals intricate details, turning faint smudges into structured, dynamic stellar nurseries. Each new detection, especially those from the highest redshifts, chips away at the enduring mysteries of the first billion years. With Webb's infrared eyes, we are no longer just confirming distances. We are conducting detailed chemical autopsies on these ancient galaxies, measuring their elemental abundances and mapping their growth, using the brilliant flash of the burst as our guiding light. We are moving from simply knowing that the first stars existed to understanding how they lived, how they shaped their surroundings, and how they died. The future of this exploration is brighter than the bursts themselves. Next-generation missions like ESVAM and the proposed Theseus Observatory are poised to find these cosmic beacons in even greater numbers, building a statistical picture of the early universe that will allow us to move from studying individual curiosities to understanding the population as a whole. We stand on the threshold of answering questions that have puzzled humanity for generations. What were the very first stars truly like? How quickly did the first black holes grow to such immense sizes? The data streaming in from our telescopes is not the end of a story, but the thrilling beginning of a new chapter in cosmic archaeology. As we look up at the night sky, it's a remarkable thought that the darkness between the stars is not empty, but filled with the faint, ancient light of these colossal explosions. Each one is a testament to a universe of constant change and incredible violence, a universe that is simultaneously chaotic and ordered. The quest to understand gamma-ray bursts is a powerful example of our innate desire to comprehend our origins, to trace our lineage not just through biological evolution on Earth, but through the cosmic evolution that made our very existence possible. So, the next time you gaze at the stars, remember that you're looking at a dynamic and evolving cosmos, one where the light from a dying star at the edge of time is still reaching us, inviting us to keep looking, to keep questioning, and to stay forever curious about the vast, beautiful,